Good afternoon, everyone. Thanks for making the trek up the hill. And welcome to our symposium, which is sponsored by the UCLA Space Institute and the annual meeting of the Meteoritical Society. My name's Kevin McKeegan, if you don't know me, and my first pleasant task is to introduce the Dean of Physical Sciences and the Executive Dean of the College, Miguel Garcia Garibay, for a few words.
Thank you, Kevin. Well, yeah, so good afternoon, and thank you very much for joining us for this special Space Institute Meteoritical Society Symposium. Exploration, missions, and sample returns from asteroids, moons, and planets. I can't wait to learn about all of that. As Kevin said, my name is Miguel Garcia Garibay. I'm the Senior Dean of the College and the Dean of the Division of Physical Sciences. And it is in that capacity as Dean of Physical Sciences that I get to interact very strongly with the faculty, students, and researchers in all of our 6 departments, and several institutes and centers that constitute the division, including the UCLA Space Institute that is co-sponsoring this event. I'd like to just mention briefly our faculty, researchers, and students are really the engine for real-world advances that positively affect our lives in so many ways. Technology, engineering, creativity from our students and our faculty have been really important in making UCLA a successful university. Our research, their research, at UCLA serves as the basis for discovery and innovation, actually stimulating our state, national, and global economy in the process. Now, the Space Institute is a transdisciplinary and interdisciplinary UCLA community. Again, faculty, researchers, students, very important, seeking to elevate space science through fundamental space physics research, technological innovations, holistic education, and engagement with the space sector. For decades, UCLA has advanced space science, planetary exploration, and technological innovation. And in light of the unprecedented investment in the space sector from government and industry, also considering the geographic location of UCLA, the impact and the access that it has on a really huge, very diverse talent, really makes us positions us in a way that we can really contribute, and that's what we hope to do strongly in areas of space exploration, science, and technology. So today we join the Meteoritical Society in co-hosting this incredible event. The Meteoritical Society is an international organization with members from 52 nations dedicated to promoting research and education in planetary science, with emphasis on the study of meteorites and other extraterrestrial materials to further our understanding of the origin of our solar system. In fact, as you can see, this event takes place in the middle of their 86th annual meeting here at UCLA. So I take this opportunity to also welcome all the members of the Meteoritical Society who are here as delegates. And really with that, all that remains for me to do is to ask Kevin to come back to the podium and help us get this going. So thank you very much.
Okay, so let's get this going, shall we? So I'm very pleased to introduce our first speaker, who is Dr. Lori Leshin, the director of the Jet Propulsion Lab. And Lori will tell us about JPL solar system missions, and we'll get your slides back up here.
Also former UCLA, right?
Also, that's right, former UCLA postdoc and Ruby faculty fellow.
Hey, good afternoon, everyone. It's a pleasure to be here to help kick off this great symposium in the middle of the fabulous Meteoritical Society meeting, which I used to attend all the time, and it's really a thrill to be back in the company of so many friends from the MetSoc and also friends from UCLA. I had a great experience here back many moons ago in the early part of my career, but this place really did help launch me, I guess, pun intended. But I only have 15 minutes, and JPL has a lot going on, so I'm gonna just jump in here quickly. I call the talk "Dare Mighty Things Together." That's kind of our motto at JPL. we're an R&D organization that's all about pushing the frontiers of space exploration. And so we're constantly trying to do things that have never been done before, but none of us do those things alone. And so the word together, to me, is really important. Everything we do in trying to explore the frontiers of space is a team effort. And people involved in the Meteoritical Society, involved in the Space Institute here at UCLA, are all part of those extended teams. You can see here one of my favorite little space explorers. That's the Ingenuity helicopter on the surface of Mars, which yesterday completed its 55th flight in the thin Martian atmosphere. Just quickly, for those of you that don't know about JPL, right here in the LA Basin, we are exploring the frontiers of space. That is something that dates back almost 87 years at this point, to the mid-30s, when a bunch of, frankly, people at Caltech kept blowing things up, and they said, why don't you go up in the hills there in the Arroyo and do your work up there? And JPL was born, working initially on rocket propulsion. And then pretty quickly we switched over to caring more about what goes on top of the rocket than the rocket itself. We did, in fact, build and launch America's very first satellite back just after Sputnik in 1958, Explorer 1. So I kind of call us the OG New Space Company, America's very first satellite. And from that, immediately after, within 6 months, NASA was founded and born, and JPL became a part of NASA. We are a part of NASA and also a part of Caltech. We are about 6,500 people strong, working up on the border of Pasadena and La Cañada, Flint Ridge. That was our history. Today, here's what we look like. Here's our family portrait. So we explore, many of you know us for Mars rovers and exploring the solar system, and that really is going to be what I focus on today. But I do want to make sure people know that we also work on big telescopes. We built one of the instruments for the James Webb Telescope, and we're still flying several telescopes, and we'll be flying more in the future. Things that are grayed out on this diagram are things that are to come, and things that are sort of more solid are things that are already flying. But most importantly, we also have a lot of missions studying our home planet of Earth, understanding how Earth is changing, tracking greenhouse gases, tracking changes in biomass on the Earth's surface, tracking water, both on land and in the oceans, to understand how Earth is responding to our changing climate, and helping to predict how we can better adapt to that change and how we can perhaps reverse and change it. But space, the solar system, is really what I want to focus on today, some of the things that we're working on currently. This symposium is really kind of about sample analysis, the power of that. I learned that here at UCLA. The way that we do that, the way that we analyze materials from other worlds, there's kind of three versions, right? One is we look at meteorites, the things that Mother Nature kind of delivers us mostly for free. Those are great, but it's whatever selected that comes at us that we get to analyze. We analyze things in situ, that is either on the surface or in orbit around other objects, to understand their chemistry. And the sort of ultimate thing we can do with the space mission perspective is to actually go somewhere and bring something back, a sample return mission. So I'm going to kind of be talking about the second two of those. The rest of the Meteoritical Society is talking a lot about the first one, about work on meteorites. So this idea of analyzing things in situ, that is at another world, goes way back. We've been doing it for 50 years, since the days of Viking. The Viking missions, which actually analyzed materials from the surface of Mars. And we have since then been going back to Mars to really greatly try and understand it. But one of the things we learned by doing Viking was that there are shortcomings of in situ measurements. You can't package up all of the incredible analytical equipment in everybody's laboratory in this, just in this room, and send that to Mars. You just can't do it. And so by far the best thing, even going back to Viking, even 50 years ago, people were saying, what we really need to do is the round trip. We need to go to Mars, get these rocks, and bring them back to Earth. And so you're going to hear a lot more about that mission, both a little bit from me and also from another talk later in this symposium. But our in situ sort of geochemical analysis does go back to Viking and even slightly before. To focus a little bit on things we're doing today, I'm going to talk about a couple of missions that are going to visit objects and not come back, not return samples. One of the most exciting is being built at JPL right now called Europa Clipper. Europa Clipper is going to go into orbit around Jupiter and study this most fascinating moon of Jupiter called Europa. It's an icy world with, we believe, a global ocean underneath its icy shell. And Europa Clipper will be doing things like taking pictures and using radar to understand the structure of the ice. But it will also be tasting the atmosphere around Europa and searching for different chemical fingerprints of what Europa is made of. And so in that sense, it is an in situ chemistry laboratory as well. Here it is. This was last week, I believe. It might have even been earlier this week. In the clean room in the high bay at JPL, we are currently building this sort of school bus-sized spacecraft with solar arrays that are the size of a tennis court, or a basketball court, actually. It'll actually be the biggest thing we've ever launched. You can actually go online on YouTube. If you look up Europa Clipper Clean Room, you can actually watch us building it. It's got a live camera stream in there all the time. All the instruments, the sensors are up there on the top. Oh, I probably have a pointer here, don't I? Yes, all up here on the top. So stay tuned for Europa Clipper. It's launching a year from October, and we'll get out to Jupiter towards the end of this decade. And then we're going to learn a lot more about this incredible moon that may be an interesting potential habitat for life, an ocean world like the Earth. I'm not going to talk very much about this one because you're going to get to hear from the PI of Psyche in a minute, but our next launch coming up in less than 2 months' time is a mission to a metal asteroid called Psyche. The first time ever we'll have visited a metal world. We've seen icy worlds and rocky worlds, but never a metal world. And Lindy Elkins-Tanton from ASU is here, and she's going to tell you a lot more about it. But we will get some great compositional chemical information about this asteroid when we get there, based on, again, the sensors that we have on board. And I just had to put this in because I was literally last week in Florida, where the spacecraft is getting ready for its launch. That's me in a bunny suit with Lindy's beautiful spacecraft in Florida. So that's launching October 5th is when the launch period opens. It launches on a Falcon Heavy, NASA's first Falcon Heavy launch. So that's the 3-core booster, right? Launch up, the 2 side cores are going to fly back to Cape Canaveral. If you happen to be anywhere in the Florida region, I recommend getting your tail out to the Cape because it's going to be quite a show. So this is an incredible mission. You're going to get to hear more about it from Lindy. Future, as we look to the future and actually talk about sample return missions, there are 2 that we are working on right now at JPL. One is a lunar mission, and this is just getting started. It's at the very beginning phases of us thinking about it. Interestingly, you might say, we have rocks from the moon, don't we? The astronauts went there. Yes, we do. But in fact, there are many parts of the moon that we have not yet sampled that will teach us so much, not only about the moon's history, but about the solar system's history. And so a bunch of our scientists, or not our scientists, a bunch of scientists had a kind of crazy idea, which they said, listen, we're sending astronauts back to the moon, which is great, but they're not going to go to the far side of the moon where we think the most interesting rocks are. So here's what we think we should do. We think we should build a rover that can autonomously drive, say, a couple thousand kilometers on the moon. Again, the Mars rovers have driven a few tens of kilometers, so it's much, much more long-range rover. Pick up some samples as it goes along, and then deliver them to the astronaut crews that will be hanging out near the south pole of the moon. I think this is a brilliant idea, a way for robotic missions and human missions to work well together. So keep your ears open about Endurance rover. That's going to be a really exciting mission for the future. But as I wrap up, I just want to talk about Mars. again, coming back to the dream that started back in the days of Viking, of doing the round trip to Mars, of bringing Mars rocks back to Earth. This turns out to be very technically challenging, which is why it's taking us 50 years to get to it. It also is scientifically challenging. We wanted to make sure if we were going to invest the resources to bring things back from Mars, that we would make sure they're really scientifically great rocks. Any rocks would be interesting, but we want to get the right ones to be able to really answer the important questions about whether life got started on Mars, about the geological and volatile history of this incredible object. And so right now, step one of Mars sample return is happening because Perseverance rover there, you see in her beautiful selfie, is driving around in a beautiful dried up lake bed with a sort of a river delta and sampling fascinating rocks, which Minnie Wadhwa is going to tell you about towards the end of this symposium. So stay all the way to the end because you get to hear about the very cool Mars rocks that sit inside these tubes that look like little lightsabers, but each rock sample is about the size of your pinky. And now our job is to go get them. And that's really what Mars sample return is all about. This is sort of a technical picture. That's Perseverance. We're going to send to Mars a big lander that's kind of like a launch pad, and laying down inside of it is a rocket. And Perseverance is going to drive up, we hope, and transfer, say, 30 of these tubes with rocks in them to come back to Earth. If that sounds confusing, let me show it to you in video form before I wrap up. With dramatic music. This will be by far the largest thing we've ever landed on the surface of Mars. There's Percy, she's already there. Probably wouldn't actually be taking her last sample when we land, but that's okay, dramatic license. She's looking up, hey, who's that? We are gonna land close by to where Perseverance is. Percy will drive up with her wonderful cache of samples she's carrying in her belly. And we'll transfer them one tube at a time into a volleyball-sized thing that sits on top of this rocket that we've just landed on the surface with this large lander. She says, I'm getting out of Dodge. And then we're going to launch a rocket from another planet for the first time. And we air launch it, because why not? It's a two-stage solid rocket that carries the samples up into orbit. First stage separates, second stage puts them into a very stable orbit around Mars. And again, it's about the size of a volleyball. Along comes an orbiter being built by our colleagues in Europe. It's a big collaboration. We capture it into the world's most complicated catcher's mitt. And then the whole orbiter comes back to Earth, where it drops off the capsule a couple of days out from Earth. And the current plan has that landing in Utah, which of course we don't show in the video. So that is Mars sample return for you. The samples are there, they are waiting for us. And now it's our job to go and get them and bring them home. The video doesn't, of course, show the most important thing, which is all of the scientists in this room jumping up and down when those samples land back on Earth. It's going to be an incredible thing. So there's excitement in the future here about both exploring objects in our solar system remotely and also bringing those samples back to Earth. And you're going to hear a lot more about all of this in the rest of the symposium. At JPL, we really think of ourselves as serving the broader space science community to accomplish missions like this, things that seem impossible, and we're thrilled to do it. So I'm happy to be here and excited to hear what's going to be said in the rest of the symposium. But don't forget, let's go bring Mars home. Thank you.
So our next talk is by Dr. Nancy Chabot of the Applied Physics Laboratory in Johns Hopkins University, and also the president of the Meteoritical Society. Woohoo, exactly. And Nancy's going to tell us about NASA's Double Asteroid Redirection Test, the DART mission.
Well, thank you. It's really a privilege to share DART with this audience here today. As Laurie so nicely said, all of these are giant team efforts, and I'm just one part of this very large team. If you're talking about DART, there is no way that you can start a talk other than on September 26th of 2022, the day that humanity first deflected an asteroid. So with a million people, over a million people worldwide watching NASA TV, this spacecraft hurled at 14,000 miles per hour towards a small asteroid that had never been seen by a spacecraft before. Guiding itself autonomously here at Johns Hopkins Applied Physics Lab, a lot of celebration, years of effort going into making this possible as the spacecraft sends back these final images on its collision course with this small asteroid. Sending back until just right until the very end. A ton of celebration. This had been a huge moment. People had wanted to demonstrate that you could deflect an asteroid and potentially keep one from hitting the Earth in the future if you needed to for years. And this was the first demonstration of that. And it was rightfully celebrated enthusiastically by many of the large team that were involved. While we were celebrating and having an amazing party, LiCiaCube was working. So LiCiaCube is the light Italian CubeSat for imaging of asteroids. It was contributed by the Italian Space Agency. It's a small little CubeSat, small little briefcase-sized spacecraft. And it had been kicked off the DART spacecraft 15 days in advance. And it made its closest approach by the asteroids roughly 3 minutes after DART impacted into there. And so what you're seeing, it had to hold those images on board and then send it back in the days and weeks that followed. But we've put them together here into a movie. And you can see it's seeing the asteroid, and then it turns away, and it's seeing, and as it gets to the asteroid, this will replay again, you see all of this ejecta, the rocky debris thrown off because of this collision. So here is a LiCiaCube approaching, seeing the asteroid getting closer, seeing the ejecta thrown off as it then turns around, captures the backside of it, and really a spectacular accomplishment for a CubeSat in deep space in order to witness this moment for this asteroid deflection. That movie is really great, but I also like to just take one frame because I think when you see the movie, you don't appreciate just what an amazing data set it really, truly is. And so what this is just one frame from that movie, but it's been contrast stretched by a factor of 2. So you can really make out that fine detail, and you see such a complex pattern of ejecta radiating out in this beautiful pattern, and you can see the complexity of this scene and just what an amazing and rich data set this is for everybody to examine. But it wasn't just LiCiaCube that was working, it was actually telescopes around the world. So here we've had over 6 telescopes involved in the DART observing campaign, located literally on all 7 continents and in space, have been involved to maximize what we learned from this first opportunity to deflect an asteroid. And this wasn't by accident. We always were planning the DART mission such that telescopes would be a critical and foundational asset in order to understand what was going on with this first demonstration of asteroid deflection. So here you see DART launched off the Earth, and it stayed in a trajectory that was pretty close to the Earth, actually. And then it approached the Didymos asteroid system. And so you can see the timing of DART's impact in September of 2022 was this unique opportunity when the distance between Didymos and the Earth were at a minimum. So it's still 7 million miles away, no need to be concerned, but the telescopes were able to get amazing data at the time of impact and for the months that followed. And amazing data they indeed did get. So the telescopes in Africa were the ones that were positioned to look up at the night sky and capture the moment of DART's impact. So what you're seeing here is from South Africa, and this immediate fast plume of material ejected off the surface. And so while we were celebrating at Johns Hopkins and while LiCiaCube's working, these were also making their way on social media, and just another very clear indication around the world of the success of DART crashing into this asteroid. Telescopes in space, here's some examples from about 5 hours later. HST, Hubble Space Telescope, and JWST. This was the first object they had both actually looked at the same time, and you can just see, again, that complex rays of ejectas a few hours afterwards. And as that initial ejecta cone, it actually goes out into a tail. It evolves out into a very long tail, and this is a spectacular view from a telescope in Chile acquired 2 days later. And then this is also from Chile, from the Very Large Telescope. And what you're seeing here is a movie that captures the first month of the evolution of the ejecta. And so as the tail develops, so once DART hits, there's immediate brightening of the system. You have this very large ejecta cone, and then it goes out evolves into a tail over this whole month that happens afterwards. Skipping ahead, because we don't have all day, but we have a lot of telescopic data, and it's really amazing. This is 52 days post-impact, and this is from Arizona, the Lowell Discovery Telescope. A really obvious tail. Telescopes around the world are seeing this thing, amateurs and professionals alike. And the tail has been measured to be over 70,000 kilometers long, and the amount of material that's estimated is about 10 million kilograms that have been ejected off of the asteroid. This is from December then. Hubble Space Telescope actually looked at this a number of times. In this one in particular, it was looking really deep in there. So here we are still 60 plus days after impact. And what's unique about this one is, along with the tail, is you see these little bright blue dots other places, right? You might think, oh, those are background stars. They're not. They are boulders that are thrown off during this impact event that are there in the system. So Hubble is seeing these meter-sized boulders in these images. Going forward, this is in March of this year, 2023, and you can still see that there's a tail. It's still there. Lowell Discovery Telescope still looking at it, and I wanted to show this one. This is one of the last images that we'd be able to get, because now Didymos, of course, has gone on to the other side of the sun from the Earth, and so we have to wait until 2024. But this last one taken by Hubble, even at the end of June and July, there is still a tail. It's still visible. It's still evolving. We're still learning so much from this system. But of course, the point of this, as spectacular as the ejecta wasn't just for the telescopes to look at the ejecta, but to figure out how much was this asteroid moved. And that's why this was always such an elegant test to do this with this double asteroid system. So you have this large asteroid named Didymos, which means twin in Greek, and about 780 meters, and Dimorphos, which is about 150 meters. These was discovered by ground-based telescopes, and Dimorphos goes around Didymos like clockwork, 11 hours and 55 minutes, 11 hours and 55 minutes, measured extremely precisely from ground-based telescopes for decades. And so using that then, what's going to happen is the DART spacecraft comes speeding in at 14,000 miles per hour. LiCiaCube kicked off 15 days in advance. DART slams into Dimorphos. LiCiaCube goes by, captures those images that you were just looking at previously. And that collision alters the orbit of Dimorphos around Didymos ever so slightly. And the telescopes get back to work. What is this orbital period now? And they make this measurement, and they find that the orbital period has been changed by 33 minutes. So now it is 11 hours and 22 minutes. And I'll put that into a little bit of context here in a second. But I first want to point out this was made by two independent methods. The first one is sort of this light curve method, which some people might be familiar with. That's because in the optical telescopes, the Didymos and Dimorphos system only ever look like a single point of light as seen by these optical telescopes. But the brightness changes with time. So if you make a graph of brightness versus time, and look, sometimes when Dimorphos passes into Didymos' shadow, this Dimorphos eclipse event, you get a dip in the brightness. Or sometimes it makes a little shadow onto Didymos itself, and you get a dip in the brightness. So by mapping that out, you could tell it was 11 hours and 55 minutes beforehand, and 11 hours and 22 minutes now. The second is from planetary radar. So planetary radar was also used for this opportunity, and what's great about planetary radar is it can get direct signal from both asteroids independently. So here you see Didymos in the yellow box, and then you see direct images of Dimorphos in this radar data. And what you see also then is that this position of Dimorphos relative to where it would have been if DART's collision hadn't happened was in a different place, completely consistent and also giving you the same answer of a period change of 33 minutes. So what does this mean, and why did you have to do this on a real asteroid? Well, seeing how much ejecta there would be was one of the main unknowns. Models had been done, but how would a real asteroid in space react to a test like this? So the no ejecta case, nobody really thought that was going to happen, but even if you hit this small asteroid in space head on, which you had never seen before, a major accomplishment in itself, you would have gotten a period change of about 7 minutes. And so 33 minutes is a lot more than 7 minutes. This ejecta is giving you this recoil effect. It's helping to enhance the amount of deflection. And when you carry that through with the geometry, we think this is a momentum enhancement factor of a little bit over 3, maybe 3.6 if you assume the same density for Didymos and Dimorphos, where you're getting so much more than just the momentum that the spacecraft speeding in at 6.1 kilometers a second brings. You're also getting this enhancement. In fact, the ejecta is helping you deflect this asteroid even more than just the momentum that you bring in directly with it. So taking that result, the team then is looking at the topography, recreating the exact way that the spacecraft crashed into the surface, because we want to know what we did to this asteroid Dimorphos, but more importantly, you want to understand it to potentially apply it to the asteroid threat in the future if you needed to use this. And just sort of one example of a simulation of sort of that are being run on the team right now of this, hydrocode impact modeling state-of-the-art facilities where you take that geometry and you crash it in there and you're getting this complicated ejecta pattern that is reminiscent of what you're seeing in the LichioCube images. This is telling you things about the strength and what this material is made out of, and this is really work that's going to be going on for a while. And it's always important, though, to put this into context. DART is just one part of a much larger planetary defense strategy. You can't do anything about the asteroids if you don't know where they are. DART works about asteroid deflection, not destruction. So this is a 33-minute period change. It's spectacular. It's still only about a 5% change. We didn't really do that much to this asteroid. You don't want to do very much, but you want to do it years in advance, decades in advance, preferably. A small nudge that adds up with a big change in position with time. So searching, detecting, tracking, characterizing, understanding what you're dealing with. Planning and coordinating, dealing internationally. This is an international issue, and you need to be doing that. Assessing the constant threat. And then mitigating, that's where DART comes in there. Having some tools in your belt that you can use if you need to potentially prevent an impact with the Earth. And we're overjoyed that the European Space Agency has a mission called Hera that's scheduled to launch next year and get to the Didymos Dimorphos system in 2026, and then in 2027, make these detailed measurements of the mass of Dimorphos and see what we did to the surface. Is there a big impact crater? Is the whole shape distorted? What is there? And that'll give us a lot more insights. And it really has been international cooperation for an international issue that is planetary defense. The investigation team has over 300 members, over 100 different institutions, representing 28 different countries that have contributed to this study in order to get what we were doing out here. And it's just really been, it's been gratifying to be one part of this team working together for a purpose like this. And going back to sort of this team theme, which I think anybody who works on these projects has to come back to, this is when the spacecraft started to come together at APL. It's May 2020. I think everybody remembers what it was like in May 2020, where we all were becoming more isolated from each other. But working on a project like this, which was so much bigger than any one person could do on their own, really, for me at least, was very rewarding to have a purpose and something that was forward-looking and that really made people come together in order to accomplish this. And LichioCube was one of the last things on the spacecraft, but it made it across the Atlantic Ocean, over from Italy into August. And this is one of my favorite pictures of the DART spacecraft before it went off and launched in space, because it's a very human-sized spacecraft that was sent on a mission to move an asteroid. And I'll just end with this, going back to September 26th. This is 4 hours before impact. This is when the autonomous navigation turns on. Nobody still has ever seen Dimorphos. All you're seeing is Didymos. The spacecraft is speeding towards Didymos, and you turn on the autonomous navigation. And it's only 50 minutes ahead of time that finally you distinguish Dimorphos from Didymos, autonomously firing the thrusters to ensure that you hit that small asteroid as close to the surface as you possibly can. And here it fires its thrusters all the way until the final 2.5 minutes. Here at 4 minutes out, you can still barely see features on these small asteroids because they're small and you're coming in so fast. It's in trying to ensure that it's going to hit Dimorphos, not Didymos, which it was aiming at before. The thrusters are now done. Its fate is sealed. It's going towards the asteroid. And here, in the final sort of minute, is when you make out the surface of Dimorphos. Images streaming back to Earth, 1 per second, shown here live. And these final images working the last second, even down to the final last sub-second, sending what it could. And that's DART. Thank you.
Well, next, I'm pleased to introduce Dr. Linda Elkins-Tanton from Arizona State University, where she is Vice President of the Interplanetary Initiative, and she's also the Principal Investigator of the Psyche mission. And she's going to tell us about the Discovery mission to asteroid 16 Psyche. Lindy.
So like I always say, I know it's painful and inconvenient, but could you keep your fingers crossed, please? It's only 49 more days of that. So unlike the beautiful DART mission, unbelievable, we have this gorgeous artist's interpretation, but it's very, very important for me to start by reminding everybody that we've never seen Psyche. We don't have pictures of it. There it is. Did you recognize it? You figured out which one it was. And so, we've got shape models, gorgeous shape models. I'll show you one in a minute. But this really is primary exploration. We've never been to a body that we believe to have a metal surface. So we're going to see it for the first time all together. And in case I would forget to say this later, we've already got the software pipeline written such that our images are going to be live on the internet for the world to look at within a half hour of our receipt. We're not going to edit them. We're not going to cut out all the things that look like bones or smiles or whatever. People can interpret them however they like. We want to share the excitement of space exploration right away so we can all look at this together. So as asteroids go, it's a pretty big one. It's about the size of Massachusetts without the Cape. And the surface area is similar to the state of California. So in the end, we're going to orbit for 26 months. This is not sample return. We're not landing. Psyche is really far away. It's hard to do those things with something so far away. But imagine flying over the surface of California for 26 months and trying to understand what California is. That's really what we're going to be doing. So we do have a number of beautiful shape models, including this one from Shepard 2021, comparing to previous Shepard and Perret et al. And sorry to keep making jokes, but it's kind of irresistible. I always say that Psyche's shaped like a potato because potatoes come in many shapes, so I'm not wrong. A number of quite talented teams have taken very wide amounts of data to create these shape models and give us a sense of the volume, which gives us the density, which is so important. And the shape models are not all in agreement. They're all in agreement that it's not a sphere, but we're going to learn more when we get there. And you could imagine that one of the challenges is then we have to create stable orbits on a body whose gravitational field we don't know yet. And so you'll see how we're approaching that later on. Now, where is Psyche? It's very far away. It's 3 times farther. At its closest, it's 3 times farther than Mars is from the Earth at its closest. So at the most distant, when it's on the other side of the sun from us, it's about 650 million kilometers. And when it's closest, it's about 250 million kilometers. Now, why would I point this out? Partly because of these quite fabulous headlines, of which there are dozens, if not hundreds. Notice that this top one is from Forbes, and the next one is from Smithsonian, and you've probably seen them even in the recent weeks. This is the asteroid that's going to make us each a billionaire. And I know with this audience that you know both that these are fabulous headlines that get a lot of readership, and that there is zero truth in them. In fact, there are so many ways that this is wrong that it's hard to even count them on your fingers. But it does get people excited, which is also fine. And it's good to note that Katie Camaro at the Miami Herald worked really hard to get the story right. Asteroid Psyche won't make you rich. It's not going to hit the Earth, but we have another reason to visit it, which is the science. And pointing out how far away it is helpful for us all to put it into context. All right. This is one of my favorite kind of graphs, which is something versus year of publication. That's how you get to see how our thinking has changed. So you can see back around the year 2000, there was even an estimate that Psyche's density might be 11,000 kilograms per cubic meter. It's hard to quite imagine what that material would be. It would be really great if that was the case, but especially after our selection in 2017, there was a lot of interest and a lot more data, and so we're settling down. Our team's estimate is in yellow there. We think it's around 4,000 kilograms per cubic meter, and so you can see between the red lines, enstatite, which is one of the candidate rock materials that Psyche might have, and then troilite, iron sulfide, which we expect, and a lot of this originated with Nancy's work on the immiscible liquids of the crystallization of metal cores, and that immiscible liquid as a metal core crystallizes the oil in the water. The oil part is basically FeS, and so troilite is an important mineral for us to look at, and then camosite, one of the typical iron-nickel metals. So we lie in between troilite and enstatite. At the time that I made this graph, maybe this has changed, this is the audience to correct me, Psyche's best measurements had it as the densest known asteroid, denser even than Cleopatra with its best data at that time. Most asteroids fit into that gray box on the lower right at less than 3,000 kilograms per cubic meter, in fact, quite a bit less. So that's our first line of evidence for saying Psyche must be made partly of metal. The reflectance spectra also show very little or no iron oxide, no FeS, no Fe2O3. So we have something that's metal and something else that's not metal, void space, rock, sulfur, carbon, something that doesn't have a lot of or any iron oxide in it. And so you all would understand that this is a petrologic conundrum. And it turns out spectrally, this is work that Stephen Dibb did, the meteorites that best fit Psyche by far are the CB chondrites, which is really kind of craziness. So we will find out what it is. And of course, our best guess is that we had an innocent planetesimal that was being smacked by objects and broken and then freezing from the outside and creating magnetic field, erupting that FES onto the surface, and being knocked over on its side. The spin axis is more or less in the ecliptic. It's kind of a rotisserie asteroid. And I always ask, all these years, I've asked audiences like yourselves, what else could it be? And my favorite alternative hypothesis for getting high iron enrichment is just very reduced material that never melted and differentiated. But it doesn't really match any of the meteoritic samples that we have. And so it's an interesting question. It's something unusual, and that's just currently our best guess. And so our first objective for science is to determine whether Psyche is a core or if it is ... question mark, something. And so I hope that all of you will be working on this with us. Important to mention that we have this fantastic student collaboration and public engagement effort. The day that Thomas Zurbuchen called to tell me that we are selected, which was a completely surreal moment. And Hal is nodding his head because he got the call that day too. I don't think we've ever really compared notes on that. The next thing he said to me was, we want you to re-propose your student collaborations and do something bolder. Now, it's easy to get a risk rating if you're doing student collaborations of certain kinds can give you a risk against the spacecraft, and you don't want to do that because that lessens your chance of selection. But after selection, you can really go for it. So we proposed 10 different programs to NASA, and they chose 4. We have a big senior capstone program. We have free online courses. We have a local science outreach with student interns. And then we have this art program, Psyche Inspired. Every year we choose 16 student artists out of a pool of applicants, and we fund them to create 4 original works of art over the course of the year. Now, we're doing this 7 years now. These are 2 examples. There are so many amazing things, and I don't have time to talk about them, but they're very tempting to talk about because they're so much fun, and they're on the website. We've had so far over 1,500 undergraduates at 58 colleges and universities participate in this program, and we really, really enjoy it. We've even published peer-reviewed articles about the pedagogy in case anybody's interested. So thank you for letting us do that. This is a little tiny part of our team. At peak, we had over 800 people active on the team. I think right now we've got around 350, maybe half of them are at JPL. Over the years, over 2,000 people have worked on Psyche, and this is something that's come up already in the 2 talks before me, and I want to stress it. This is one of the greatest joys, is doing work in giant teams where no single person understands how the whole thing works, but together we can create these miracles. And often this is a kind of work that isn't done by individual academics, and that's a loss, because it's absolutely great to be in the mode of wanting the whole team to succeed. So we lead the mission out of Arizona State, and our mission manager is Jet Propulsion Laboratory. Our contractor to make the spacecraft bus and the solar panels, ours is the size of a tennis court as opposed to the basketball court, so the sports analogy for JPL is going strong. 25 meters across these solar panels will be when they unfold. And then we're getting magnetometers from Danish Technical University and the gamma ray and neutron spectrometer from Johns Hopkins, APL, and then cameras from Malin Space Science Systems. And then we have many, many other partners who we all value hugely. Now, we are going to launch in 49 days on a Falcon Heavy, 7th Falcon Heavy launch, first for NASA, as Lori said, and they are going to re-land the side boosters, and I have witnessed it, and it is mind-blowing. And then, as many of you know, we were going to launch last August, and we were not ready, and we went through the astonishing process of deciding and then convincing people that we weren't ready. It's hard to convince people that you're not going to be ready. And then going through review board and continuation review and being approved for October 5th through 25th of this year. So many lessons learned, and I'm really happy to talk about it with anybody who's interested in this process. And I'll also say that the IRB report that is available freely online at NASA is unredacted. It's exactly the real report, and in my opinion, they really, really helped us and got it exactly right. So I can't say that all that often about review boards, so I'm thanking everyone who worked on it. So we are going to zoom around the sun and get a gravity assist from Mars in 2026, and then we're going to sneak up on Psyche in 2029. So it's 5.8 years to get there, and then 26 months of orbiting. And the orbits are going to go like this. We're going to start far away so that we can remember physics. You're either teaching it or you took it, where it's so convenient to be able to treat something as a point mass. So we'll start that way at an orbit where we can treat Psyche as a point mass, and then we will work our way down and then do a plane change maneuver in order to get the final very close orbit for the gamma ray data on composition. And in each of these steps, we're going to be learning about the gravity field. You can imagine this is an object that is not a regular shape, and it's probably made of two materials. One material is twice as dense as the other, and we don't know how they're organized. They could be finely mixed, which would make it seem homogeneous from a spacecraft distance, or it could be half the body is metal and half the body is rock. We could have a really wonky gravity field. And so one thing we had to do was demonstrate that we'd be able to find a stable lowest orbit no matter what. So we did 1,000 Monte Carlo simulations of what Psyche's gravity field might be and prove that we could always find orbit D. So that was a fun part of the analysis that we did. Now, I don't have beautiful pictures of Psyche yet, obviously, but I have beautiful pictures of hardware. So I'm going to just whip through the story of Psyche hardware because I think that many of us are hardware geeks, and it's fun to see. So this is the shipping container for a spacecraft, and maybe some of you have never seen one before. They're a mobile clean room with duplicate generators, so they never lose their power supply. They're fully instrumented. They're absolutely sealed. And on the side of this one, which is Maxar's, it says, "Spaceflight hardware do not drop." And I really laughed about that for a long time until, I'll show you later. We didn't drop it. We didn't. This is Henry Stone, our project manager at JPL, and me right after it came down from Maxar to JPL for integration. Beautiful high-gain antenna there in the clean room. And here's the Deep Space Optical Comm team. We're flying this tech demo that does laser communications instead of radio communications. That's going to be a great thing that we get to practice with during that time that we're going around Mars. And it's really designed for Mars distance. We joke that we're going to get Netflix to Mars after this technology is perfected. And that team did an incredible job. Just a hero shot of the spacecraft. You can see the big booms coming out. Of course, we have to keep the magnetometers that are up there on the top right and the gamma ray spectrometer, which will be later in later pictures installed on the bottom right, away from the main bus of the spacecraft. These are our Hall effect thrusters. This is the first use of Hall effect thrusters outside of Earth-Moon orbit. Hall effect thrusters use magnetic fields to accelerate the ionized xenon noble gas as opposed to regular ion thrusters that tend to use electric fields. And this is what they look like on the left in the thermal chamber being tested. So it's going to be this beautiful blue haze of ionized xenon, and that's how we get out there, totally solar electric. Now, how do you test for electric and magnetic interference and compatibility? You have to put the spacecraft into a Faraday cage and eliminate all the outside fields. So what you're looking at on the left, of course, is the spacecraft, and on the right is a giant Faraday cage made of conductive carbon fiber fabric. So the spacecraft went in there for its testing. It's things like this that I just love learning about. It's so much fun. So I was watching from the gallery in the giant clean bay at JPL, because this whole thing is a clean bay. And then we have to do the thermal vac testing, put the spacecraft under flight conditions in the sense of temperature and vacuum. And so see the person up on the top left standing on the balcony, and then a person down below in the lab coat. You can see how big this is. This is JPL's big thermovac. That bottom gold part of the spacecraft is the adapter ring that connects us to the rocket in the end. The spacecraft's being put inside, the giant door shuts, and then the whole 25-foot diameter thing gets evacuated and kept at space temperatures with an endless parade of liquid nitrogen tankers coming up through the gate at JPL for days and days. And so that was a really great thermal test for us. Then we get flown to Kennedy on a C-17. And so this is the moment when I suddenly thought, you could drop it. You could drop that. Look at that. This is how they bring it off. I'm so glad I didn't know that before. Could we have a solid ramp? No. Okay. And so we had to make sure that our shipping container fit into the C-17. It fit with very little room to spare. And this was one of the many, many interesting things you go through as you're building a spacecraft. We couldn't use the Maxar shipping container because the Maxar shipping container is a little bit bigger, and they fly it on an Antonov. And NASA doesn't provide Antonovs for flight. And we wanted not to ship it across the country on Route 10. In the past, there's been at least one spacecraft that was shipped across Route 10 that arrived at Kennedy with bullet holes in the shipping container. And so I really wanted it on an airplane. And so what ended up was we built a shipping container for us and some other missions. And that was a whole adventure to itself. But it worked beautifully, got us there. And so here we are in Astrotech Corporation doing the final closeouts for assembly, test, and launch ops, and we've just finished all of those closeouts. We had to then, the solar panels were off at Maxar for further testing, and then they came back just, 10 days ago, and got reinstalled. And so here they are coming off. That's one panel. Each side has 5 panels, so it gives you a sense of how big they are. And there they are being installed on the side of the spacecraft. So beautiful, these solar panels. And then tested to make sure that they were going to extend properly. And then finally, this is a picture from earlier in the mission. This is me and our ATLO manager, Brian Bone, sitting under the spacecraft, and he's pointing with his flashlight where the comms panel had just been installed at that time. And so on Friday, after our pre-launch media day, for which I was down in Florida on Friday, it was bagged up and moved to the hazardous processing facility where it's getting fueled up with that totally hazardous stuff, xenon. We're flying over 1,000 kilograms of xenon for our propellant. And then we go through closeout, and in just a couple weeks, encapsulation. I'll be there to watch it, see it for the last time, go into that fairing, and then we'll be launching. And then we'll all be waiting for that moment when we get the pictures of Psyche and we know what it looks like at last. Thank you so much.
So our last talk before our break is by Dr. Hal Levison from the Southwest Research Institute and principal investigator for the Lucy mission, and he's going to tell us about Lucy in the sky with asteroids.
Okay, so Lucy is a reconnaissance of a population of asteroids called Trojan asteroids. These are asteroids that lead or follow Jupiter in its orbit by about 60 degrees. They're interesting because they're the leftovers of the formation of the outer planets. Matter of fact, small bodies themselves are interesting, and this is why we're spending so much time studying them, because basically they're the fossils of planet formation. If you want to understand how these planets formed, you need to go to the small bodies. Indeed, we named Lucy after the Lucy fossil. You can see that in our motif. We have a lot of references to the Lucy fossil. Lucy was launched on October 16th, in 2021 at 5:34 in the morning. It was still dark. It was one of the most beautiful launches. People who live there said it was one of the most beautiful launches they've ever seen. I'll show you some pictures. We're going to visit 2 main belt asteroids, one coming up in this November. It's a little scary. Another one in 2025, but then between 2027 and 2033, we're going to have 5 encounters with Trojan systems for a total of 8 asteroids. 8 Trojans. So we're going to 10 asteroids with this mission. That is a record. So let me start off talking about the scientific motivation for this. And I have to admit, right, I'm a theorist by training. I'm a very weird principal investigator for our mission. So I'm going to go into why this is interesting scientifically and what it tells us about planet formation. But I always put this bullet up here to remind me to tell you this is a mission of exploration. We've never seen a Trojan up close before. We have no idea what it looks like. And unlike other small body reservoirs in the solar system, the proximity of the Trojans to Jupiter means we do not get any meteorites from this population. So we're really clueless as to what it's about. And one of the surprising things we learned when we started to study these things from the ground is it's not a homogeneous population. Despite the fact that they occupy these little regions of space, they're very different from one another. There's several ways of looking at this. We can use spectral classifications, which is basically the color of these things in the visible and near infrared. We find that there are basic three types. There are P-type asteroids, which are sort of reddish, D, which are very red, and then there's this smidgen of gray stuff mixed in. This is going to be part of my story in a few minutes. Another way of looking at this is albedo. This is visible albedo. That's the fraction of light that is reflected by the asteroid versus a near-infrared albedo. And you can see a lot of variation here. These objects go from basically dark to really, really, really dark. They only reflect about 3% of the light, visible light that hits them. This diversity, I think, is telling us something fundamental about the history of the solar system. I think these objects formed in different regions of the solar system and were embedded in the Trojan swarms as the planets formed and moved around. But in order to understand what this population is telling us about the history of the solar system, we have to understand the diversity. So the first thing we need to do to study this population is to go to a large number of objects that cover the diversity and try to figure out what that diversity actually means physically. And that's what Lucy is going to do. And we do this with this amazing trajectory. The guys who figured this out, they're truly artists, a combination of science and art to figure this out. What you see here is Lucy's trajectory and a rotating frame with Jupiter. So you imagine you take a camera, put it on top of the sun, and have it rotate every 12 years so Jupiter stays in the same place. This is what you would see. The actual trajectory of Lucy looks like this, where we launched in an orbit that is very similar to the Earth's in 2021, and then we use a bunch of what we call Earth gravity assist to slowly pump up the aphelion, the furthest distance of the spacecraft from the sun, as a function of time. Right now we're sitting right around here. But let me go back to the rotating frame. So as I said, we launched, rattle around the inner solar system for a while, have a couple of Earth gravity assists. On the way out, on the first orbit, like I said, we're here. We're going to go by a small main-belt asteroid called Dickenesh. That's the one that's in November, and I'll talk a little bit about that. I should have said earlier that we named Lucy from the fossil Lucy because of the connection about learning about connection with understanding our origins. Dickenesh is the Ethiopian name for the fossil Lucy. Then we're going to come back in, have another Earth gravity assist. It's going to kick us out into the Trojan swarms. On the way out, we're going to encounter this main belt asteroid called Donald Johanson. We named that after the discovery of the Lucy fossil. Go out into the leading swarm, have 4 encounters with Erybetes and its satellite Keta, Polymele and its satellite we nicknamed Sean, Leucus, and Ors. Come back into the inner part of the solar system, have another Earth gravity assist, which is going to take us out to the Menenius Patroclus binary in 2033. So here are our rich targets. Again, I said the key is the diversity. So we have 2 C types, 1, 2, 3, 4 P types, a D type here and a D type here. So we're covering all the known spectral types. By the way, we're doing all this in only 15 months. It's going to be a hell of a ride. I already showed you this plot. This is the albedo, visible albedo, near-infrared albedo. The gray represents the diversity of the Trojans, and these are our targets, and you see we cover that diversity. But there are a couple of these objects that are interesting in and of themselves, and we're going to talk about a couple of these first. Let's talk about Erybetes and Keta. Erybetes is really interesting because it's the largest remnant of the only disruptive collisional family in the Trojan swarms. We've never visited an object like this. Planets form by a combination of dynamics and collisions. So to be able to actually study a byproduct of a collision is going to be interesting. What's more, Erybetes is a C. Remember, I showed you this pie chart that shows the Trojans are about half Ds and half Ps, with about 7% of the objects being Cs. And most of the Cs are in this family. What's that telling us? I think it's telling us something fundamental. I can think of two things. The first is that whatever makes these Ds, these very red objects, is very fluffy. And when there's a collision, it goes poof, and it's gone. So we see no family. The other idea is that whatever makes these things red is only skin deep. And when you take a red object and break it open, it's going to be gray on the inside. That's what I think the answer is going to be. Lucy will be able to test this because the second hypothesis, the young craters which penetrate into that surface should be gray. So we should be able to see that right away. The other object, I have lots of targets in this mission. They're like my children. Everybody says you shouldn't have a favorite child. This is my favorite target. By the way, I have a favorite child too, but that's a different. Right? We are going to visit a near equal mass binary. These are two objects about 100 kilometers in diameter. They're almost spherical on a circular orbit around one another, with a distance separating them of around 700 kilometers. Here's an HST image of this. It's not resolved. You can't see the objects themselves, but the fact that they're the same brightness tells you they're roughly the same size. This is really cool because while these type of binaries are very rare in the inner part of the solar system, and by this inner part, I'm talking about inside the orbit of Neptune, if you go out beyond the orbit of Neptune into a region that we call a cold classical Kuiper belt, almost all the objects we see there are near equal mass binaries. So I think that's telling us that whatever formed the first macroscopic things in the solar system tended to form these binaries. If that's true, then our binary, the Patroclus binary, is actually a remnant of that initial population that happened to survive the planet formation process. And that makes it very interesting. So what's Lucy going to do? We're covering a lot of real estate, right? We're covering these 8 asteroids, or 8 Trojans. We're spending most of our time traveling from one to the other. This is a 12-year mission, and all the science is being collected within about 24 hours. The rest of the time, it's just going from one object to another. And we're not stopping. We're not even orbiting. We're just flying by. So we have to do everything we possibly can in one of these flyby encounters. And that's what we're doing. We're going to be studying the surface geology, looking at color and composition. We're going to be able to measure their mass, and combining that with the shape, we should get bulk densities. We're looking for satellites and rings. And we're doing this with a suite of instruments. By the way, this is the spacecraft. To put this in scale, this is about 2 meters in diameter. From wingtip to wingtip is 50 feet. The science instruments are sitting on this articulating platform. There are 4 or 5, depending on how you count. We have a high-resolution panchromatic camera supplied to us by APL. Terminal tracking system, these are wide-field imaging cameras that are mainly for navigation, supplied to us by Malin Space Systems. We have a thermal infrared spectrograph by ASU. And then we have a RALPH, which is really 2 instruments in one. It's a color camera and a near-infrared imaging spectrograph. This is the wavelength we're going to cover. We go from about 4,000 angstroms all the way out to about 50 microns. That puts the solar arrays to scale. Right, these are really big, right? We're going further from the sun than any other solar-powered spacecraft in history. I've never seen one of these in person. I have seen that. Matter of fact, I'll show you pictures of that. So let me go on to some eye candy. This is what we call this instrument pointing platform with the instruments. Here's the Ralph. Here's the thermal infrared spectrograph, our panchromatic camera, and our 2 navigation cameras sitting here. By the way, this was built at Lockheed Martin in South Denver. Here's the completed spacecraft on a shake table, right? We shake it to mimic what it's going to feel during launch. Nothing fell off, thank God. But again, you can see the, this is running out of batteries, but you can see the folded up arrays, and you can see the high gain antenna on the instrument. By the way, I'm going to show you this in a minute. These solar arrays are made out of cloth, right? And so folded up, they're only 4 inches thick, and that's sitting in there. So here's the array. They're so big that we couldn't open them both at once at Lockheed. Every time we'd open one, we do one side and then flip the spacecraft over to do the other side. And here's an image with a light underneath it. You can see everything that's sort of gold color here is simply cloth. Here we are down at Astrotech, right before we encapsulated the spacecraft. Here's 4 of our team members. Which one's me? Can you tell which one's me? This is just a beautiful picture. Somebody went in one side of the fairing and took a picture of the spacecraft looking the other side of the fairing. This is on our way to our launch pad. By the way, this was a ULA launch. And then before launch, we got some interesting well wishes from people.
A little noisy, but I'm so excited. Lucy is going back in the sky with diamonds. Johnny will love that. Anyway, if you meet anyone up there, Lucy, give them peace and love from me. And NASA, peace and love. It's just so great that we're heading out. I loved it when we reached Mars. Now we may be going a little bit further. It's a lot of room. Peace and love. Don't forget, my name is Ringo. Peace and love.
Like he needed to tell us who he was. He added it on in the end because he realized he didn't say. It's very funny. I got a chance to meet him a few months ago, which was quite exciting. Here's some pictures of launch. Like I said, it was at night. And you can see one of the spectacular things about it is we had these bank of clouds. So the rocket sort of disappeared into the cloud bank and then erupted like Close Encounters of the Third Time. So you could see the arrays of God and things like that. It was quite beautiful. Now, I was so close that to me, it just disappeared into the cloud bank and I never saw it again, right? But there are a lot of great videos of this online. You should go take a look at it if you're interested. We've done some science. Even early on, we observed this lunar eclipse, right, that occurred in May of 2022. Right, what you see, here's the Earth, and you can see it rotating. This was taken over about 3 hours. And then you could see the moon moving into the Earth's shadow. That's pretty cool. We also took a lot of observations during the first Earth gravity assist in October of 2022. Right, I love this picture because we tend to, when we go out and it's a full moon, you think, wow, how bright the moon is, right? This is real scale, and you can see the albedo of the moon's only about 7%. It's actually really dark, right? And you can compare it to how bright the Earth is. Imagine what our evenings would be like if the albedo of the moon was similar to that of the Earth. During the flyby, we took some high-resolution images of the moon. We wanted to determine really how large a crater we'll be able to see on the Trojans. So this was a test of our systems. But we ended up with some beautiful images there. So our first encounter is going to be this November. It's very exciting. This is a target of opportunity that we put in order really to test our system. This is very complicated. It has a pointing software on it, very similar to the DART system, and we want to make sure it's going to work. So we're doing these 2 main asteroid tests. We added this one, Dinkinesh, which was named after the fossil Lucy. It is in the inner edge of the asteroid belt. Semi-major axis is about 2.2 AU. It's an S-type asteroid, and if we assume the albedo is about 0.22, that gives us a diameter of about 1 kilometer. This makes it the smallest main belt asteroid to be observed by a spacecraft. So I'll end by just talking a little bit about our heritage. Right? NASA has a history of putting plaques on their spacecrafts. Remember, Pioneer 10 and 11 had messages to aliens. Well, it turns out I'm a dynamicist, right? I do long-term evolution of things like comets and asteroids in the solar system. The first thing that I did when we got the orbit of Lucy is put it in a computer to try to figure out what's going to happen to Lucy. And it turns out we're leaving it in an orbit very similar to the one we're doing our science in, right? Where the closest approach distance is about 1 astronomical unit. Where the Earth is, it's aphelion. Its closest distance is about 5.7. Turns out that's stable for an average longer than 2 million years. So it's just going to sit in that orbit for a long period of time. So we decided, rather than sending messages to the aliens, that we would leave messages to our descendants. So we reached out to cultural leaders throughout the world. We have Nobel laureates in here. We have US poet laureates in here. Amanda Gorman, if you remember her, she spoke at Biden's inauguration. We also have all the Beatles in here, the ones that are living, gave us recent quotes, right? And then we took some quotes from people passed away, Carl Sagan and stuff like that. So we are leaving that for our descendants. Hopefully someday, you can easily imagine 1,000 years from now, 10,000 years from now, 100,000 years from now, our descendants send out astroarchaeologists trying to find out about our culture. And so we left them on Lucy for them to find. So where is Lucy now? Here is the orbit of the Earth, Mars, Jupiter. These are all our targets, and you can see Lucy is heading out for its rendezvous with Dinkinesh, which is shown right there. And so I'll end with that. Thank you. I have a question
Well,
for
I
you.
mean, go ahead. That's really unfortunate. I think everybody in this room agrees with that completely. I'll say it's been really interesting on DART, right? Because DART is a planetary defense mission, and it's received very differently than a science mission. We here, when we were talking about this, we see the similarities, we understand the similarities. So I'm not saying or trying to tell you how to do that, but we have found very different audiences and support. And on DART, we would very rarely get asked, why are you doing this? Why are you spending taxpayer dollars? How much does it cost as compared to the science missions that I've worked on before? And so that's been refreshing and potentially is an overlap between science and also relating it directly to aquability.
Yep, we've been trying to get a mission that's a lunar orbiter, which would be doing magnetometry at super low altitudes. It's really cute. Laurie, I really want to talk to you about it. Unfortunately, the only way I can sell it is looking for ore deposits on the moon. So, which is
Yeah, so we do talk to all the other space agencies. I met with people from the New Zealand Space Agency actually yesterday here on campus, and we definitely talk to Australia as well, and this is an ongoing topic of conversation, Phil, and I agree with you. I think as they get better established, my hope is that they'll expand the aperture, but it's great to see a space program really going in Australia too. I mean, even that wasn't true a decade ago, right? So it's quite exciting.
Okay, we have some people on this side over here.
Tim McCoy from the Smithsonian. So this was spurred by Lindy's talk, but really to all of you. This is a bittersweet meteoritical society. having since post-COVID with the passing of John Wasson and Roy Clark and Ed Scott and really Joe Goldstein, the titans of iron meteorites, that we are now losing that generation. And so the question I really have for you is, what would you say to the most junior among us for the future of planetary science and meteoritics and the connection between those two?
This is such a challenge for the way that we compete missions in the U.S. Because you get judged often by the strength of the science team, judged by, senior accomplishments, and it's hard to start with a really young science team. But one thing that we're working on with NASA, and that Tim, you and I have been talking about, and I feel like it's like a softball because you invited me to talk about this, is that especially with our longer mission, it's incredibly important both for our team and then for the community that we be giving more junior scientists opportunities to be apprenticed up in this system. And one very important thing we learned from headquarters is that it is not a requirement of NASA headquarters that junior collaborators be at the institutions of senior co-Is. They don't have to be at the same institution. And so we are putting together a program that is not ready to announce, and I don't have the details because we're just a little busy getting to launch, but we have found some resources, and we're going to bring junior people onto the team to be apprenticed with us, and allow our senior people eventually to roll off and retire, still come to meetings, but then give their budget to junior people. And so this is maybe some nice steps in that direction.
Can I just say also, you're going to hear in the next session too about additional missions that are coming up. In some ways, like the world of the asteroid-meteorite connection and the world of sample return missions, it is exploding in the best possible way, I really feel like. So much more. The knowledge that we had of what asteroids were like up close 15 years ago was almost nothing, and now we're, again, going to continue to blow that out of the water, and we're getting samples back from OSIRIS-REx in a month, and Mars moons and Hayabusa, and it's incredible, and then Mars ultimately. So I actually think it's a really exciting time in this scientific field. Maybe that's too Pollyanna, and I probably have to be to have the job that I have, but I think it's a really exciting time.
Next.
I cut you off last time, and go ahead, and then I'll say something quick.
My only advice is to follow the science and follow what you're interested in doing, rather than have an ambition of being involved with a mission. Right? As I said before, I'm a theorist. I think most of you know that. A lot of you do. And ended up just walking my way into this because I realized we were in a position where we now are idea rich and data poor. Right? But I did that through trying to understand my research. So I just think you should follow what interests you. And if it ends up that you are involved in the mission, then that's great.
Yeah, and I think this is a really interesting time for our society, for the Miracle Society, because we have done great science since 1933, as we've been talking about that this meeting. But now it's the underpinning of so many priorities for space nations around the world that the samples are really driving a lot of that data there, and the people in this room are the ones that have that foundational knowledge in order to do that. So I think it's a real opportunity for everybody in here to not just be studying what we have in our hands, but also forming and shaping this next generation of space exploration, and so I hope people are energized by that. I'm energized for that for our society.
Yes.
I think
Yes.
you
Now
all,
Denton.
to follow up on Hal, I think you all exemplify what can accomplish with passion and coming at it from the passion side rather than I want to do a mission. But I have a question for Hal, it's more detail, I guess, or for all of you at some level. Once, we know missions have a scope, they have an end date of the nominal mission, but we all know there's been some great science done by missions like Stardust, for example, imaging the deep impact target. Will we get more? Can we get more Trojans out of those orbits? And for any of the other panelists, is there a glimmer in your eye of what's perhaps achievable beyond scope of mission?
Well, remember, Lucy's 12-year mission. So I'll be 75 at the end of mission. So while if the spacecraft is healthy, right, there are other options people can go to. It won't be me.
Well, there's
But if
those young
are
people out
interested,
there.
yeah.
No
That's gonna
more
be an
data
option.
coming from the DART spacecraft. In case you were wondering
Okay,
about that.
it's a gimme.
But I really do hope that DART is just the start of this planetary defense mission line, and that it really is setting the way. And we heard about NEO Surveyor on Monday, and then other missions going forward from there. I think that there's a lot of important applied science that can be done in this area. So I'll consider that DART's legacy.
For Psyche mission, of course, we're a long way away from approval of mission success and for an extended mission, but our most likely extended mission would be to just orbit closer and closer to the surface and get better and better data of Psyche, because there aren't a lot of other close-by things that would match our propellant load at the end of our mission.
Can I go? Oh, I have a question.
Yep.
Over here.
Yes.
So I have a question for
And you
Nan.
are?
This is Miriam Tellis
I
from
know it is, but everyone else needs to know.
Miriam Tellis from UC Santa Cruz. I have a question for Nancy and then one for Lindy. So for Nancy about DART, do you expect the boulders that are kind of swarming the Didymos, is it Dimorphos or Didymos? I forget. Do you expect them to be reaccreted or lost from the system? And then for Lindy, I have so I know you're going to have a gamma ray. You have a gamma ray spectrometer. What are you looking for at the surface of Psyche?
Yeah, so ejecta, staying in the system versus lost. So the giant tail is lost. Those boulders that you were looking at have escaped the system, are moving very, very slowly. But that's only the limit of what Hubble could see in there. We fully expect that there are smaller objects in there. Some of them will reaccrete. The Hera mission is taking this very seriously. And so they will approach slowly and see what's there. I think this is a really interesting aspect of it. I thought, I should have known better, but the question usually would be like, and when are these going to hit the Earth, and did you make a giant problem? They're not a threat to the Earth. It's okay. None of those boulders are going to come and impact us. But it is interesting to see how a natural object, that we all know that these are likely weak objects, rubble piles, there's the size of a sports stadium, how they actually reacted, how they fractured. We're going to learn a lot from that. So those boulders that you saw there are largely not going to reaccrete, but other ones will. And when Hera gets there, we're so lucky to have this follow-up mission to really go and see Didymos, the larger one, and Dimorphos, the smaller one, and with a spectrometer, with an orbiter, with all the proper instruments to really see which stuff's fresh and which stuff's new and which stuff's not. So it's going to be really interesting, Miriam.
Gamma ray spectrometer, an instrument I had no idea existed before getting involved in space missions. What an amazing instrument that is. So we will get, the reason we're flying a gamma ray spectrometer and not a near infrared or some other sort of spectrometer is because we needed to be able to measure metal. And so that is what we're going for. And we'll be measuring iron, we'll be measuring nickel. It gives you atomic proportions and a bunch of other elements. But the biggest hope is that there would be areas of metal that are large enough that we can get a fairly high fidelity composition for them and understand the nickel content, because that will tell us whether that part of Psyche was an early crystallizing or a late crystallizing part of a core, if it was someplace in the middle, or if it was just strangely reduced material that didn't go through a normal core fractionation. So that's one of our biggest questions with the gamma ray spectrometer.
Other questions looking out there? Okay, well, I sort of had an observation that leads to a question, and that has to do with, I was really struck with the remarkable diversity of objects that you were all talking about. And I guess I'll direct this mostly at Nancy with DART. How much do you think we'll be able to generalize from the DART mission in understanding the physics of objects like that, and then will we be able to apply that to the other objects that we're exploring in the solar system? From a defense point of view, I would say.
Yeah, I mean, I think, DART really is just the start. It was the first step towards developing a technology. It doesn't mean that we're in an operational capability in order to do this yet. There's nobody in their right mind who would say that the momentum enhancement factor is 3.6, and that's what you should plan on to avoid an impact with the Earth. But is it always bigger than 2? For example, and this is sort of what people are wondering, can you always count on at least that amount of recoil that you're getting there? Operationally, of course, people talk about multiple spacecrafts. You wouldn't just have one thing sent out there. You could hit it multiple times, multiple years. The key to planetary defense, though, and really the success for all of this, is finding the asteroids, finding them early, having that warning time to be able to do smart things about it. And so while we appreciate the diversity of asteroids, I think everything that we're learning from science, and there are some differences, there are also sort of similarities in those size, and putting yourself in the position to take this first step to do a first test, see that the ejector really is contributing so much, is potentially likely something that people would count on. But again, it's there's still a lot of work to do, and that's why really, if after NEO-Surveyor there's not other missions that follow on to further demonstrate this technology, then I think that'll be a failing in some ways.
Thank you. All right, then, sure. This gentleman is from the American Museum of Natural History in New York.
Thank you.
Didn't
Thank you,
mention that
Kevin.
last time.
So as meteoriticists and as curators of meteorites, what areas of terrestrial research on the rocks we have would be most useful to you in understanding both rocks you've already impacted or rocks you're about to look at?
So the meteorite research is really an underpinning of planetary defense. So the fundamental measurements that people have made on the strengths of the materials, the different densities, these are used in people's codes, that do the asteroid threat assessment project in order to do that. So the work that's been done by this community is already being used. That said, how do you take the hand sample and turn it into something like Dimorphos, right? That's why we needed to go into space in order to do this in-flight test in order to do that. But that doesn't negate the fact that the meteorites are always the underpinning and really giving us that understanding for these objects and how they would react. And it's a great resource going forward for future things. People also bring them into high impact facilities, and shoot at them and see what happens. And so there's a lot that you can do here on the Earth that obviously you can't do in space, and then that underpins the exploration going forward.
Great, okay.
My name's Todd Hansen. I'm potentially moving into science communication, so I was interested in your presentation. You're talking about there's $19 quintillion of asteroid metal is out there. Everyone can now get rich, and those are two fairly credible publications which made that mistake. So I'm curious about your thoughts on how that happened, how you worked with the other reporter to get it right. And I'd also like to use an example. James Webb has been looking at early galaxies, and suddenly everyone was saying the universe is so much older than we thought it was. And if I'm not mistaken, I think there's independent, separate confirmations of that, maybe cosmic microwave background radiation, correct me if I'm wrong. But there were credible scientists that are appearing all over the place that were saying the universe is so much older. I won't name any names because half the room probably knows these people. But it just seemed like they were jumping the gun. So I'm worried from my perspective, how uninformed am I, because I'm an English major, trying to communicate this perhaps. But also there were some scientists out there that seemed to be jumping the gun a little bit. So I'd kind of like to get an overall perspective on that.
Well, I can just admit in this, secret room that it is my fault that these numbers came out, because after I actually don't regret it. I think it's a very fun calculation to do. PBS NewsHour during the 10 hours of endless interviews when we were becoming like oatmeal brains after selection. PBS NewsHour said, well, if it's made of iron and nickel, like if you could bring it to Earth and sell it on the metals market, what would it be worth? And I thought, well, that's a fun calculation. So I did it. And so it is $10 quintillion, 2017. But of course, we have absolutely no technology to bring this asteroid back. And if we did, it would probably be catastrophic for the Earth. And then there would be nobody left to buy the metals. And then even if we did successfully bring it back and not destroy the Earth, which would be the goal, then the metals market would be flooded and it would be worth zero. And so, I would just say that I think there are a lot of writers out there who did not take the Hippocratic oath of do no harm with their journalism, and they're really just not even trying. They're trying to get clicks. And so you obviously are a person who is trying to use some sort of logic and evidence-based knowledge and doing your best. And it does not matter what your background is. If you're a logical, responsible human being, you'll get the answer pretty right. And so I talked especially to the reporter from Forbes who writes the space column, And I said, you know, it would be great if you could stop talking about how Psyche's going to make us all billionaires, because it's really, really, really not. And he said, but I'm a science writer for Forbes. I've never had so many readers before. You know, so like there's the pressure of the marketplace, which makes so much sense. And then he did actually explain in his columns how that was a wrong idea. And so it was, and I don't mind that, but I think that it does teach us buyer beware, all of us. I think we all have the tendency to not believe anything we read in our own field and to believe a lot of what we read in other fields. I think we have to not do that.
Yeah, I agree, but the way to deal with it from your perspective, I think, is peer review, right? Just get on the phone, especially if you read something that you think is BS, and I've read a lot of stuff recently that I think is BS, right? Having somebody call me up and say, what do you think? I'd be happy to spend the time to talk to you and tell you why it's not right. So I just encourage you to do that.
I mean, I think we can all fill the vacuum too, right? I mean, that's on us. And so I think one of the things that has been really exciting for DART is we did have this 300-person team, and we gave everybody the power and the talking points and going out there and doing that, right? I mean, and so I think, you know, if all of the programs make an effort to enable the whole entire team to effectively represent the mission and talk about it, you fill that space up and meet people where they're at. Like, I take every Bruce Willis joke that you send at me. That's awesome, right? Because it's an opportunity to talk about something that you're interested in, right? So take the interest that you're getting from those clicks and then use it there. But I think it's also on us to not just complain, but to fill the vacuum, right? We can do that, and I think we can do that effectively, and then that's what people are really hungry for, because they're interested at the end of the day. That's why they're clicking.
100%. And don't trust headline writers. Headline writers are the source of a lot of the challenge. If you actually read the articles, they're often much better, but the clickbait is the headline writers, who are often not the authors of the articles, actually. So beware of the headline writers.
Well, with that sage advice, beware of the headline writers, I think I'd like us to thank our panelists and speakers again.
My name is Minchang Liu. I'm the co-chair of the Meteorological Society meeting and from Lawrence Livermore National Laboratory. Then, we're gonna switch the gear a little bit. So the first half of the symposium, we talk about space missions, but for the second half of the symposium, we're gonna be talking about return sample missions. So for the first talk of the second half, it's a great pleasure to introduce Professor Shogo Tachibana, who is a professor at the University of Tokyo and JAXA. So he's going to talk about sample return from asteroid Ryugu.
Thank you very much. So first, I thank Kevin and Minchang for having me here. It is a very great honor for me to give a talk about the Hayabusa 2, which is a sample return mission from a carbonaceous asteroid Ryugu. Okay, so why do we want to go to small bodies to bring back samples? So those small bodies are the remnants. Small bodies in the solar system are the remnants of the first object formed in the early solar system. So they will keep the information on the very initial state of the solar system. And they are the first object formed, so they gave the initial physical and chemical condition of planet formation, including the Earth. So those small bodies may answer these very important science questions. How did the solar system form? Why is the Earth habitable? How did life arise, and from what? One of such small bodies is C-type asteroid, which is abundantly present in the asteroid belt located between Mars and Jupiter. And there had been a hypothesis that C-type asteroids are the parent bodies of carbonaceous chondrites, a group of meteorites, and record the early evolution of the solar system. For instance, through the study of carbonaceous chondrites, we know the age of the solar system. And some of carbonaceous chondrites contain organics and water in the form of hydrous silicates. So if the carbonaceous chondrites are from C-type asteroids, those asteroids may have brought water and organics to the early Earth to form the ocean and to arise the life. But the hypothesis should be tested. So the JAXA, Japanese Space Agency, decided to visit one of C-type asteroids, Ryugu, to bring back samples to the Earth for detailed analysis. This is the image of the about 1 kilometer sized Ryugu asteroid, which is about the size of the campus, and having a spinning top shape, and its bulk density is 1.19 gram per cubic square centimeters, which is a little more than the density of the water ice, but lower than typical meteorite densities. And there are many boulders on the surface, and the presence of those boulders and its relatively low bulk density suggests that Ryugu is a rubble pile body formed by reaccumulation of broken up pieces of the ancestor body. And its surface is actually really dark, and the spacecraft found the ubiquitous OH vibration feature at 2.72 microns, which indicates the presence of hydrated silicates in Ryugu rocks. Okay, and then there were many boulders, so it was really hard for the team to find a good place to go. And this is one of the safe-looking place surrounded by dangerous boulders, but the team was brave enough to go there, and then we did this sampling operation twice. The first one was made here, and the second touchdown operation was made nearby the spacecraft-made artificial impact crater, and the spacecraft succeeded in making about 15-meter-sized crater on the surface of Ryugu, and then we expected to collect some subsurface samples as an ejector of these impact experiments. And the movie on the right shows how the spacecraft collected the samples. When the spacecraft touched the surface of Ryugu, it shot a projectile. And under the microgravity condition, the ejector was stored in the sample canister here. And then this is the capsule that returned to the Earth. So these two movies are real movies of the touchdown operation. You see that so soon after the spacecraft touched the surface of the asteroid, it went up back to the space. And this is the first touchdown operation, and this is the second touchdown operation. And after these two successful touchdown operations, the spacecraft came back to the Earth with samples in December 2020. And at that moment, we realized that the spacecraft was healthy. So we decided to extend the mission, which is called HAYABUSA-2 SHARP. SHARP is the acronym of a small hazardous asteroid reconnaissance probe. And this is the mission for the technical challenges of long-term space navigation, but during which we're going to try to observe two small asteroids. We're going to make a flyby observation of 2001 CC21, which is an S-type asteroid in 2026. And we are going to explore 30-meter-sized, very small asteroid 1998 KY26 in 2031, of which rotational period is 11 minutes. So it's a really quite fast rotator. So we are really looking forward to seeing two new small worlds with this HAYABUSA-2 SHARP mission. So coming back to the sample, and this is the photo of the sample container coming back from Ryugu. And when we opened that container, we found really dark stuff inside. And so these are the samples so bringing back from the asteroid Ryugu. And in the first touchdown operation, we collected about 3 grams of samples, and for touchdown 2, we got 2 grams of samples. So 5 grams, in total, 5 grams of samples are brought back from Ryugu. Okay, and then the project decided to use 6% of the total mass, which is 0.3 grams, for detailed analysis. And we try to understand what the Ryugu is made of, and then what Ryugu samples record about its history in the context of the solar system evolution. We had 6 sub-teams analyzing the samples in detail using different techniques. And about 400 people, researchers and grad students contributed to the analysis from all over the world. I really thank all the people who joined this analysis activity. So now I'm going to talk about the result we found from Ryugu samples. And so far, we have published about 50-ish papers, and now 30 papers are under review in Meteoritics and Planetary Science, which will be out as a special issue of the journal, and more papers will be submitted. And so these are the part of the samples the HAYABUSA-2 project analyzed. So most of the samples are 1 to 2 millimeters in size, except for this one. And this was the 3rd largest samples we got from the asteroid Ryugu. Along this direction, the size is about 9 millimeters. Okay, now let's take a look at the sample. So we found Ryugu sample largely consists of pyrosilicates. 90 to 80% volume percent of Ryugu consists of pyrosilicates, with carbonates, iron sulfides, and magnetites, and then those minerals are formed through the reaction in liquid water. So that means liquid water was once there in the original Ryugu. And the isotope studies of dolomite, one of the carbonates, and magnetite iron oxide showed that those minerals formed at temperatures like 37 degrees C, which is about 100 Fahrenheit, about 5 million years after the solar system formation, which is much earlier than the Earth formation. So Ryugu is a highly aqueously altered rock. And we found the real water droplet, real ancient Ryugu water trapped inside a few tens micron-sized iron sulfide grain. You see the electron microscope image of the beautiful hexagonal-shaped iron sulfide. And here are voids, and then we found aqueous fluid inside these voids. And that aqueous fluid contained CO2. And the CO2 is a really highly volatile component. So in order to have CO2 as a source material of Ryugu, so Ryugu may have originally formed in a very cold region of the solar system, in the outer solar system, far beyond the main asteroid belt. And now let's take a look at the chemistry. We will not go into details of this complicated plot, but what I want to say is that Ryugu's chemistry matches the sun. So we know that the sun contains 99.9% of the mass of the solar system. So the solar system is the sun. So Ryugu's elemental abundance matches that of the sun, except for highly volatile elements such as hydrogen and noble gas. So that means Ryugu formed from the very original chemical ingredient of the solar system. So everything may have started from Ryugu-like stuff. And so those planets start from the Ryugu, like the very original material from the solar system. However, concerning the meteorites, we have such meteorites of which chemistry matches the sun, but they are really rare. We have about 70,000 meteorites in the terrestrial collection, but only 9 meteorites called Ci chondrites matches the chemical composition to that of the sun. But Ryugu belongs to the major asteroid group, C-type asteroid. But is the parent body of Ci, which can be a chemical reference of the solar system, but the rarest type of chondrites. So how can we explain that? So probably the Earth's atmosphere may have been working on a filter, resulting in a biased sampling of meteorites on the ground. So in space, there are many CI-like stuff, so many materials having the sun's chemical composition, but they are just bound out in the atmosphere. They cannot survive the atmospheric entry. So we meteorologists may have been working on a very biased samples. Okay, so I talked about water and the chemistry, so now have some time to talk about organics. Ryugu contains about 5% of carbon, and 2/3 of which is present as organic matter. And we have various kind of organics, like organic nanoglobules, which is less than micron size, and also the organics closely associated with phyllosilicates. So those organics may have formed during the aqueous alteration on the Ryugu's parent body. However, some of the organics show the very peculiar isotope compositions. For instance, this one shows the deuterium enrichment, which indicates that very low temperature chemistry that may have happened in the sun's parent molecular cloud. This is a very beautiful JWST image of the star-forming region. And the stars from the very cold, stars formed from the very low temperature gas cloud, and within which a peculiar chemistry occurs to form these isotopically characteristics organics. And we also found many kinds of organic molecules. So far, more than 20,000 organic molecules have been identified, which includes some prebiotic molecules, such as amino acid and the uracil, which is one of the nucleobases forming RNA. So those molecules are formed abiotically. However, so prebiotic molecules are already present. So that indicates that before the origin of the Earth origin of the life on the Earth, so prebiotic molecules have already been prepared in space. So, and then now I'm talking about the gas. And the Hayabusa 2 sample container was tightly sealed. So we tried to extract any released volatiles inside the container from the samples. And we found, unfortunately, we found some leakage of terrestrial air, but we still got information, the results of the presence of solar wind noble gases. And so we could, so that gas is the first returned gas, first gas samples returned from deep space. And finally, I'm going to talk about some surface geological processes. Ryugu is thermally dead already, but the surface is still active through the process of space weathering. So the Ryugu surface is exposed to solar wind and micrometeoroid impacts, so resulting in the formation of dehydrated and once molten layer on the grain surface. So the surface of Ryugu is not a safe place at all. So this is my final slide. So we returned the first carbonaceous asteroid samples from Ryugu, and 5 grams of the sample is currently the largest amount the samples returned from deep space until next month. And Ryugu is the freshest CI-like materials that keeps the chemical original ingredient of the solar system. So potentially a very new elemental reference of the solar system. And Ryugu may have been a traveler in the solar system formed in the very outer region to the inner solar system. So its siblings may have brought volatiles to the early Earth. So I am really looking forward to the Bennu samples and the results from Hera, Lucy, Psyche, MMX, and more small body missions in the future to better understand our origins. Thank you very much.
So the next talk will be given by Dr. Lindsay Keller from Johnson Space Center, OSIRIS-REx mission to asteroid 101955 Bennu.
All right, thank you, Ming Chang, and thank you, you and Kevin, for the invite. Our PI, Dante Loretta, I'm sure would love to be here, but he's a little preoccupied and busy right now, and so I got volunteered for this, this part of the mission. Just a reminder that the OSIRIS-REx mission, we have a complex acronym where we're interested in the origins in terms of the return and analyzing a sample of a pristine carbonaceous asteroid regolith. I mean, it's the primary focus of the mission. And part of doing sample return is it provides ground truth for telescopic data, not just for Bennu, but also allows us to say lots of things about the rest of the asteroid population. We wanted to do a good job looking at sort of the resources that are available on the surface, sort of mapping the chemistry and the mineralogy across the surface. At one point, Bennu is a potentially hazardous asteroid, so understanding something about its properties and shape and mineralogy is important. And then we spent a lot of time doing regolith exploration, looking at the sampling sites at scales down to essentially the millimeter. So we launched in 2016, collected a sample in 2020, and in 38 days and counting, we should have a sample back here on Earth. So this is Bennu. It was after seeing Ryugu up close first, and then seeing this, we see it's sometimes hard to discriminate the two of them. They're both these spinning top-shaped asteroids. Both of them are rubble piles, surfaces covered in very big boulders. Bennu's a near-Earth object. It's about 500 meters in diameter with a small microgravity environment. We spent nearly 2 years in orbit surveying the entire surface, looking for great sites to go and get samples. And like I said, the sample that we did collect was done in October 20 of 2020. So just a little bit about the actual sampling mechanism. This is the OSIRIS-REx TAGSAM. This is our touch-and-go sample acquisition mechanism. We didn't physically land onto the surface of Bennu. This is the TAGSAM on the bottom of this sort of pogo stick that made the contact. When it contacts the surface, we fire nitrogen gas that generates a fluidized bed, and that collects the bulk sample that is coming back. And we're trying to collect 150 grams of samples there, so there's some extra there because the mission requirement is we have to bring back at least 60. In addition to the bulk sample, the bottom of the TAGSAM head has an array of what we're calling contact pads, sort of a secondary sample collection, more of a passive collection. These are little 2-centimeter diameter pads of stainless steel Velcro, and that's meant to trap and pick up some of the particles on the uppermost optical surface of Bennu. These are going to be really important, both as interesting samples, but also in terms of looking very carefully at space weathering and comparing that to the bulk sample that may have sampled deeper into the surface. These are just the little Velcro loops in there, and there's some particles in here that we've been practicing with. So the idea here is we collect sort of millimeter and also much finer particles as well. So like I say, we spent 2 years in orbit surveying, mapping, using our instrument suite to characterize the surface of Bennu. We identified 8 potential sampling sites. That was further down-selected to one site, and that's this site, which is the Nightingale site. It's in the middle of about a 20-meter size crater, a Hoikioi crater. In terms of the VIS near-IR spectroscopy of the site, it's spectrally redder than the other parts of the average surface of Bennu. It's also, we think, based on the cratering mechanics and dynamics, one of the youngest impact features. So we wanted to look to sort of fresh material that would be organic rich, which is one of our efforts. It's sort of at the mid-latitudes, so that it's probably not too strongly heated. We estimate the sort of peak temperature that it ever experiences about 360 K or so. And as Shogo alluded to, you get into these sites, the overarching concern is that you don't crash your spacecraft. So mostly this is considering navigation and safety considerations because we have some very giant boulders here that are the size of school buses as well. But you also had to have material in the sampling site that was ingestible by the TAGSAM. We have an upper size limit that can safely enter into the TAGSAM of a few centimeters. And the nice thing about being in orbit for 2 years is we were able to really get some really good ideas from the spectroscopy, both in terms of the VIS-NIR IR and also in the thermal emission work, understanding what was present in the material in terms of the mineralogy and particularly the organic matter. This is a little zoomed in image of the actual contact location. This image is clearly stressed, stretched, not stressed. Pardon me. I'm stressed, no. But you see this sort of salt and pepper texture. That contrast has been stretched quite a bit. This is a very dark asteroid, much like Ryugu. It's dark, low thermal inertia, but there are these sort of different morphological kinds of boulders where we have these sort of dark, crumbly, more friable things, and also more smoother surfaced boulders. And we have both represented within the area of the TAG SAM. The TAG SAM is about 30 centimeters in diameter. So we're optimistic that we'll sample at least the sort of the two major lithologies that we think are present on the surface of Bennu. It was interesting because of the camera suite that we had on the spacecraft. We get lots of interesting imagery. When the TAG SAM first contacted the surface, this is just going back and forth, we see sort of surface disruption. You see this boulder tilting and moving. This boulder, which is actually pretty good size, it's 40 centimeters long, also kind of pushed aside and disrupted. It launched some little small particles off of the surface. Basically, we had this idea that the interaction with the TAG SAM head and the sort of the boulders, we have these sort of range of strengths of the boulders that are present on the surface of Bennu. 1 second after we contacted the surface, the TAG SAM fired its nitrogen gas to fluidize the bed to drive the samples into the collection chamber. After 6 seconds, we were still moving into Bennu with a sort of downward velocity of about 4 centimeters per second. And at one point, we sort of fired the thrusters to back away from the sample collection site. So this is another image. You can see the shadow of the TAG SAM arm coming in, hitting the sample. We ended up penetrating almost 50 centimeters into the surface of Bennu. And the thrusters we fired for something like 25 seconds, and it took on the order of about 16 seconds for us to back out and get back sort of to the original surface. In that time, we generated this incredible plume of material with a lot of sort of vertical and lateral velocity compared to the surface. And much of this disruption is due to just the nitrogen gas firing, but also the thrusters from the back-away maneuver. After we sampled, there was an addendum to the mission where we actually came back and did a flyby to see whether we had left our mark on Bennu, and we had. This was in April of 2021. Had another flyby at about 4 kilometers distance. And this should be playing something, but it's not. Any rate, oh, here we go. So this is sort of the before and after. This boulder right here got shoved out to here. We pushed a bunch of the rocks and made this sort of little ridge in here. So we've done some things. I'll take a closer look at that in a little bit. And this is a nice animation that does not come complete with noisy music, so I'm not going to hum, but if you had been sitting on Bennu, you might have seen something like this, watching the actual sampling event. The spacecraft is penetrating in, and finally we fire thrusters and do our back away, but we raised a considerable amount of dust and particulate around the crater, and then safely lifted off and got back to our orbit. This is part of the TAG site, looking at the crater where we actually collected the samples. We've done some stereo photoclinometry to That's sort of the 5 centimeter scale. So we dug a pretty nice little crater here. It's basically about 9 by about 7 meters in size. We displaced something like 12 cubic meters of Bennu during this sampling event. And when you look at the cratering dynamics and the scaling relationships, we have some estimates in terms of the bulk density of the material is on the order of 500 to 700 kilograms per cubic meter. And like most rubble piles, this thing is very cohesionless. It's nice granular material. This is, again, a before and after, looking at just the spectral slope of the Nightingale site before and after sampling. We produced, there's now the presence of higher abundance of smaller particles in the tag site after sampling. The tag site, the crater is after sampling, is darker, so we've decreased the albedo a little bit. And it's also spectrally redder than the material. Obviously, that's enhanced in the images. So the freshly exposed material is amongst the reddest material and the darkest material that we've seen on Bennu. We think that is because we're exposing fresh material from deeper below the subsurface of Bennu. Material that's maybe not as space weathered and fresher than the material on the surface. So this was a happy day to get the tag SAM back into the SRC. We look and think we have on the order of about 250 grams of material with a significant error bar. That was just based on sort of momentum calculations based on the guidance and navigation team. When we look at the cameras that image the contact pad bottom surface of the tag SAM, we have 23 of the contact pads have observable particles trapped in them, or at least it was when it was stowed. We'll see what survives coming back through atmospheric entry. And parts of the interior of the tag SAM are covered in small dust. The tag SAM, I suspect, when we get back, is going to have dust all over its surface. And as I mentioned, Earth return in 38 short days. So in the interim, we've been practicing and getting good at retrieval. The tag SAM and the SRC come to the Utah Test and Training Range. Our group, the Lockheed folks with the mission and our curation team have been practicing the recovery operations, where making sure the area where the SRC came down is safe. It comes down in a bombing range, so there might be unexploded ordnance in the neighborhood. It comes back and is not hermetically sealed, so we're trying to get it bagged as quick as possible, secure it with a padding, and it is flown by a helicopter back to a temporary clean room in a hangar at the Utah Test and Training Range for packaging and safing and getting it under a nitrogen purge for its trip back to the NASA Johnson Space Center. In addition to that, we're collecting samples in the neighborhood where the SRC landed for contamination knowledge and contamination control. We don't expect that to happen, but it's good to be covered just in case. And the samples will come back by jet to Allington Field outside of NASA Johnson Space Center, be trucked on site. This is the OSIRIS-REx Clean Lab in Building 31 at JSC, for those of you who have been there, where all the rest of the NASA curated collections are stored and processed. The SRC will be disassembled here. Tag SAM will be moved into this glove box for all the curation processing. We have a fabulous curation team that has practiced this a lot this past summer and are going to take great care of our samples and get them out to the science team as fast as they can, I hope. And that science team is pretty significant. We've got something over 220 scientists, graduate students, postdocs, support personnel on 4 continents. These are sort of the institutions that are supporting the sample analysis campaign with something like 60 or 70 different kinds of instruments and kinds of analyses that will be performed during the preliminary examination phase, that first 6 months that the science team has access to the samples. And the things that we're going to explore in our sample analysis plan, we have something like over 70 hypotheses that we're going to test by the sample analysis campaign. And similar to what Shogo showed us for the Hayabusa 2 samples, we have clearly going to have materials that predate the solar system, pre-solar grains, through all this disk processing and being catastrophically disrupted into a rubble pile, achieving its sort of final shape and coming back to Earth. And we're also looking at what we've done to Bennu during that sampling event. And finally, this is from our last science team. This is just a small segment of the group. And so we are anxiously awaiting a safe return of samples from Bennu for us and for the rest of the scientific community. So thank you.
Our next speaker is Professor Tomohiro Usui from JAXA. So he's going to tell us about the Martian moon exploration.
Thank you. I'm Tomo Usui from JAXA. I am delighted to be here, and particularly delighted to be here to give a talk about the JAXA's Martian moon sample return mission called MMX to the friends in the United States and also the MESOC community. So JAXA has conducted a series of the small body explorations. The following the successful Hayabusa and Hayabusa 2, JAXA think of the two paths. One is to go to beyond the snow line and an outer solar system. And then one good example is like a comet sample return in the 2030s. The other path is stepping into the Mars program through the MMX. The sample will come back in 2029. So, what do Phobos and Deimos, the Martian moon, look like? They are characterized by a low mass and low density relative to the terrestrial Earth's moon. The density is around like the size is around like 27 kilometers for Phobos and then 15 kilometers for Deimos. And then the density is 1.87 and 1.47, which is much smaller than the typical silicate rocks of, let's say, 2 to 3 grams per cubic centimeters. So such a low density signatures imply that Phobos and Deimos would represent either a porous rocky body or have ice in the mantle. Another important signatures of Phobos and Deimos are dynamical properties. So they have very low eccentricity, let's say 0.00 something, which is pretty much the circular orbit, both of them. And also both of them has low inclination and orbital parameters almost on the Martian equatorial plane. So that kind of signature is so unique, and that like we still do not know the origin of Phobos and Deimos. Lots of hypotheses has been proposed, but still not yet decided. So two major competing hypotheses has been proposed recently. One is capture of asteroid, which is consistent with like D or T-type infrared spectra. The other is in situ formation by an impact that is similar processes to form the Earth's moon. That kind of that impact scenario favors and consistent with dynamical parameters of the low eccentricity and inclinations. So the MMX has two major goals. One is to reveal the origin of the Martian moons. The other is to observe the processes that have impact on the evolution of the Mars system. So, as you know, Apollo missions could have provided a significant insight for both lunar and the Earth. In the same manner, let's say something like a magma ocean hypothesis. In the same manner, I believe, and the team believes, that a Martian moon study would also provide a significant knowledge and observations to see the formation of both Martian moon and Mars itself and the Mars total mass system. So let's get into the spacecraft and the mission instrument system look like. So this is the cartoon showing the spacecraft of the launch configuration on the left and the cruise configuration on the right. So MMX spacecraft is the largest spacecraft among the JAXA's planetary space missions. It weighs about 4,000 kilograms. That consists of the three modules: the propulsion module of the chemical propellant in it, and an exploration module that has 4 legs to land on the Phobos, not touch and go stuff, actually land on the Phobos. In between the exploration and the propulsion modules, we'll have a return module that has sample return containers. And we have tons of actually 13 mission instruments. It's a lot complicated, but I enjoy to have lots of data will come. So among the remote sensing and in situ instruments, we have telescopic and then wide-angle cameras, and also like gamma rays and neutron spectrometer provided by NASA, and also LIDAR, and also the MILS, that stands for MMX infrared spectrometer. And also we have rover that is provided by the cooperation with CNES and DLR that also has onboard, it's very faint, but anyway, doesn't matter. So it's a Raman and radiometric cameras. We have also the dust monitors and the mass spectrometers. Also, we have on the right-hand side, you see like a sampling system that has coring system and a pneumatic sampling system. I don't want to show you that. I want to tell you that MMX is very international sample return mission, and 4 of the 13 instruments are provided by the international partners. So what's the sampling system look like? As I said, we have 2 sampling devices. One is like a coring system attached on the robotic arm, tip of the robotic arm, that has 3 or 4 cores. The size of the core is almost the same size of my thumb to access the Phobos building block to beneath the surface, about greater than the 2 centimeters. The other sampling system is attached to the footpad. And this is a pneumatic sampling system, and blow down the nitrogen gas to collect the selective sampling of the Phobos surface beneath. That may also include the Martian sample. I'll talk about that later. So the very supplementary, complementary coring and pneumatic sampling system maximize the MMX sample science. And also we have a 13 mission instrument, and then among of them, 2 of them would provide a critical information on the origin of Phobos and Deimos, actually Phobos. One example is a visible near-infrared spectrometer MILS that cover the spectral ranges of 0.9 to 3.6, which is almost equivalent to the absorption feature of the OH band and also the organics that have absorption of like 3.3 to 3.5 microns. That is, this will be a new information that to see what's the Phobos' surface materials originated in. On the other hand, and you can see on the right, we have the gamma ray and a neutron spectrometer that gives you elemental abundances of major elements of the magnesium, iron, oxygen, silicon, and hopefully minor elements, but it's like a radiogenic element of potassium, thorium. That kind of major element abundance information could differentiate the achondritic or the chondritic composition or signatures on the entire body of Phobos. And also we have a sample because it's a sample return mission. The sample analysis will tell us about the origin of Phobos. This is a table showing the expected characteristics of Phobos samples in terms of petrology, mineralogy, bulk chemistry, isotopes, and organics as a function of like capture of asteroid scenarios and then in situ formation like giant impact scenarios. I do not get into the details here of this table today, but I want to highlight a few things. One is like if it's like a capture of asteroid scenarios, the return Phobos Regulus would mimic that of the carbonaceous chondrite. We are not sure, of course, but on the other hand, if it's like a giant impact-like origins, the Phobos Regulus may contain or represents a high temperature product, let's say volcanic gases or the gas spherules, as we see in the lunar samples. And also, most of you guys are meteorological people, and you are familiar with the fact that isotope is very geochemical, could be the geochemical fingerprint for the origins. Good examples are the oxygen isotope, the capital delta 17 and then chromium 54, plus some other transitional element isotope and chromium, titanium, molybdenum, some other guys. The combination of these stable isotopic compositions could differentiate the origin of the carbonaceous chondrites matter or no carbonaceous chondrite matters, or like Earth, Mars, and the terrestrial bodies. So combination of the petrology, mineralogy, isotopes, and everything then could be used to clearly identify the origin of the, at least for the return sample, and also the origin of Phobos. So we have another bonuses. MMX will bring back not only for the Phobos sample, but also the small amount of the Martian samples, because Mars ejector could exist in the regolith of Phobos. The numerical simulation suggests that the Mars ejector on the Phobos could have experienced a much lower launch velocity than the Martian meteorites, suggesting that they could preserve the original information. And also that the Mars ejector would contain a variety of ancient sedimentary materials and hopefully organics. Let's say a good example is like lake-bed sediment and calcium sulfate veins and lake-bed mudstone and gale craters. This is totally different than what we have as a Martian meteorite, because Martian meteorite is harsh, the hard igneous rocks. So I believe that Phobos Regulus would provide a wealth of information on the ancient surface environment of Mars. And last slide, I may want to pose you a crazy idea proposed by crazy scientists, including me. And assuming that present life is present on Mars, or extinct life existed on the surface of Mars, the numerical simulation suggests that the remnant or dead remains, let's say the fossils or biosignatures, that kind of material could be transported from the surface of Mars to Phobos, and there may be a chance that the MMX will bring the dead remains of the Martian life from the Mars to the from the Phobos to the Earth, and then that remains called Shigai. That stands for the sterilized and harshly irradiated gene and ancient imprints. And Japanese, for those who know the Japanese, and the Shigai means dead remains. So, but it's still crazy idea right now, but that may become real. Anyway, this slide, I'll end up with this slide, quick look chart showing what MMX mission status look like. MMX is a Japanese next generation sample return mission from the Martian moon. JAXA is now hustling to keep the development schedules as planned for the launch in 2024. The spacecraft will stay at the circum-orbit in 3 years, 2025 to 2028, during which we will go to the Phobos and Deimos, do some remote sensing observation and in situ observation on Phobos, and also the multiple flybys observation by Deimos, and get the samples greater than 10 grams from the Phobos and return to the Earth in 2029. And if everything is happening well, and then this will be the first sample return mission from the Martian satellite. Thank you.
So the last talk of the symposium will be given by Professor Mini Wadwa from Arizona State University. She will be talking about Mars sample return.
So thrilled to be here as part of this really exciting symposium this afternoon. And thanks very much for sticking it out to the very end. It's my real privilege, actually, to serve in the role of principal scientist for the Mars Sample Return Program. And in this role, my primary responsibility is to bring these samples back that are currently being collected by the Perseverance rover, to bring them back in a state that basically preserves the scientific integrity of these samples so that, in the words of Mark Watney, you all can science the shit out of these samples once they come back. All right. So Mars sample return, this is going to be the first sample return from another planet. So it's a historic endeavor. It's been a priority since the 1980s. In fact, it's been thought about since well before that. And it's been a priority as part of the last 3 National Academy decadal surveys, and certainly will be the path breaker for the first round trip in advance of humans to Mars. The reason why we want to, of course, go to Mars is because even though we've really explored Mars in many different ways with orbiters, with landers, with rovers, we've built up this immense body of knowledge about this planet from remote observations. We've learned a lot. I mean, at the current time, this is a cold, dry, inhospitable world, but we understand from all the things that we've learned from these orbiters, landers, rovers, is that in the ancient past, say 3.5, 4 billion years ago, it was a much different place. That this was a place that had perhaps had a warmer climate, had maybe a thicker atmosphere, may have had standing bodies of water on the surface, very much perhaps like what ancient Earth might have been like. And so we really are looking at a world that gives us insight into perhaps what early Earth might have been like. In fact, we know that the early Earth may have supported life something like 3.5 billion years ago. And that's a time when Mars may have been habitable as well. And so at the current time, of course, there's less than 1%, very much less than 1% of the Earth's surface that dates back to older than 3 billion years. And of course, that's because Earth is a geologically very active planet. Plate tectonics, weathering, all of these processes are working incessantly to erase the rock record. And Mars, on the other hand, has greater than 50% of its surface is older than 3 billion years. And so that record of early planetary evolution, the formation, accretion history of Mars, the differentiation history of Mars, crust formation, core formation, the earliest planetary evolution exists on Mars, as well as possibly the beginnings of the record of life in our solar system. All of that could be recorded on Mars, and that's the reason why we want to go there. So the big picture goals in terms of the science goals for MSR, it's of course one to understand the planetary context. That's really important. If you find the evidence of life there without that planetary context, it really doesn't make any sense in terms of understanding really where life came from. And so we want to understand the planetary context, the timescales of major events, crust core formation, how long did the core dynamo last, large-scale impacts, volcanism, all of those things. We want to understand how climate evolved on Mars. We know that it was a much different place 3.5, 4 billion years ago, and how that planet has evolved, how the atmosphere was lost, how that water was lost from Mars, all of that. We need to understand that context as well. We need to understand the history of water and ancient habitable environments on Mars, and also the potential development of life on early Mars, of course, as I mentioned earlier, which will provide us with insights into when and where life may have originated on Earth. So the value of Mars sample return, of course, in terms of, it is a decadal priority. It says in our the latest decadal survey that was reported on just last year, it is the highest scientific priority of NASA's robotic exploration efforts in this decade. And that's what we're hoping to accomplish, it's because it is a priority of the science community and has been for a while. It will have global significance. It basically represents one of the most significant international collaborations between NASA and ESA, and it will pave the way, of course, to humans to Mars. It is responsive to the National Decadal Academy's recommendations, and these return samples, just like the Apollo samples, I mean, these will be analyzed for decades to come in laboratories across the world by hundreds of thousands of scientists. Inspiration and impact, of course, is another factor. We know that a lot of us were inspired by the Apollo missions bringing back samples from the moon, and that's going to be inspiring future generations. But also, Mars sample return is our nearest term opportunity to answer the question, are we alone in the universe? This is something as human beings, this is one of the most fundamental questions that if we can answer that, that would really change our worldview as human beings. And so it's one that has incredible significance. So this is basically this showing you the Mars campaign, MSR campaign architecture. And it's what's called the elephant plot. It's incredibly complicated, but it is complicated for a reason, because there are a lot, it is one of the most robotically ambitious missions that's ever been attempted. And it is a partnership, as you can see here, between NASA and ESA. You can see the NASA components that are in tan and the ESA components that are in blue. And this is a campaign that's actually already underway with Mars 2020. The Perseverance rover is already collecting rocks, regolith, and atmosphere. And basically, we already have more than half the tubes are actually filled with samples already. And that's part of what I'm going to be showing you here today as well. And the green part, that's the next part that's the one that I'm currently responsible for in terms of the work that we're doing right now. And it involves two different launches. One will be for a sample retrieval lander, which is, as Laurie mentioned earlier, it's the heaviest lander that we will ever land on Mars up to this point. And it carries with it a number of components. The reason why it is big is because it's got a number of things on it. It's got the Mars Ascent Vehicle, that beautiful video that Laurie showed of the air launch. It's got the first time ever attempted launch from another planet. It's going to have that, the capability, of course, to launch these samples into orbit. And so also, of course, it'll have the sample transfer arm, which is going to be required to take the samples from Perseverance and put them into that little volleyball-sized sample canister. And there'll also be, as a backup, sample recovery helicopters, which are basically Ingenuity-class helicopters, except that they will have mobility, some limited mobility, as well as gripping capability, so that they can grab onto these samples and deliver them in case Perseverance is unable to do it for whatever reason. And then, of course, the second launch is, well, it actually is scheduled to happen before the sample retrieval lander, but this is going to be the Earth Return Orbiter, which is going to then catch those samples in orbit around our Mars and bring them back to Earth. And that's not the end, of course, of Mars sample return, because that is just the beginning. That's when the fun really begins, because then at the end is the sample receiving project, which is when all of the sample analyses really begin in earnest, and that's where all the fun begins. So at the current time, actually, what we have in terms of opportunities for the science community to engage, we have a Mars Sample Return Campaign Science Group, and this is actually a competitively selected group of scientists. You may recognize some of the faces here. And basically, this is a group of scientists that essentially will be providing us with advice and guidance in terms of some of the planning that we're doing, especially for the infrastructure, the ground-based infrastructure that's going to be needed for the sample receiving facility, for example, as well as guidance in terms of some of the sample integrity issues, as well as we're planning for Mars sample return. And we have, of course, a number of ex officio members here. I'm part of that, as well as Ken Farley, who's the project lead for Mars 2020, because obviously Perseverance is the first component of Mars sample returns, already collecting those samples. And there's actually one thing I did want to say is that there's lots of opportunities for the community to engage in this effort. There's going to be calls for this MSPG every 2 years. There's going to be the competitively selected teams that will be involved in this. There'll be, of course, a phase 2, which will be hopefully starting sometime in 2026, when we'll be planning actually for the implementation of the objective-driven science that will be conducted as soon as the samples come back. And in the meantime, there'll be other additional opportunities as well. And you may have seen, for example, an announcement of opportunity that came out for the measurement definition team for MSR, for which we got something like 850 NOIs for that. So, we really are hoping and really want you to engage in this process and looking forward to that. So where is Perseverance at this point? As I mentioned, that is what's happening right now. This is the front end of this Mars sample return campaign, this first phase of it. Perseverance landed in Jezero Crater, as you might recollect, in January of 2021. And this is the landing site here shown within Jezero Crater near that delta front that you can see here. This is the delta front right here. This is the crater floor. The Octavia Butler landing site is where Perseverance landed. And this dashed line basically shows the traverse that Perseverance has taken during its prime mission. And this is along the path that a number of the samples were collected in the crater floor, as well as then, of course, near the delta front. And now, of course, we are beyond that extent. We're in the extended mission phase of Perseverance and still collecting additional samples. But I just wanted to give you that context here. And this is where we are in terms of making progress with collecting the samples. So Perseverance brought with it 43 tubes, sample tubes, of which 38 you could fill with samples, and 5 of them are essentially witness samples, witness materials for blanks. And so at the current time, we have filled 23 of these sample tubes, of which 14 are paired rock cores. And paired rock cores, that was actually a deliberate strategy that was undertaken by Perseverance during the prime mission. And the goal of that was to have a pair of rock samples from each rock, such that one of them could be carried on board Perseverance, while the second sample, could be deposited in the sample depot, the first sample depot, within Jezero Crater. And that sample depot would be created as a contingency, essentially as a way to just make sure that if something went wrong with Perseverance, that we always had a place to go to where we could collect those samples. And so that paired sample strategy, basically, we have 8 samples that were collected during the crater floor campaign. And as it turns out, we went to Jezero Crater because we expected actually to see sedimentary rocks at the bottom of that. It was expected to be a lake deposit at the bottom of that crater. And it was basically, the goal was to be able to sample those lake sediments as well as go to this river delta front and sample another habitable environment that way. As it turned out, we found out that actually the crater floor is most likely igneous materials. And so, from my perspective, I think this is wonderful because we have this diversity of materials now of igneous samples that we collected in the crater floor. And then there's these plethora of sedimentary materials that we have been and will be collecting in the delta front as well as the delta fan. And also, of course, we plan to collect many more materials beyond the Jezero Crater to get even greater diversity of samples. And so at the current time, we've got these 23 samples. 14 of these are collected within Jezero Crater, 8 during the crater floor campaign, 6 during the delta front campaign. And then beyond that, we've collected 3 single rock core samples most of them after the Three Forks Depot was created, where we deposited 10 of these sample tubes as I mentioned, one from each of the pairs that was collected within Jezero Crater. And among these, there's also a regolith sample. There's one atmospheric sample, which I'll show you was a serendipitous atmospheric sample, but it's valuable. And of course, a witness sample here. There are, at the current time, 20 sample tubes remaining, of which 18 can be filled with more samples, and 2 of them are witness tubes. And this is basically just showing sort of the traverse actually closer up to the delta front here. And this is where we are as of last week, Ingenuity helicopter being here, Perseverance being here, and Ingenuity actually just finished flying its 55th flight. So that is just incredible. So it's just basically showing you that these helicopters that we're planning to take with us as a backup plan, you know, it's a robust plan to be able to do that. This is just it's a beautiful image because it contains all of the 10 samples that were deposited at this Three Forks site, which is within Jezero Crater. It was about the flattest, most benign terrain that we could find within Jezero. And we were able to locate each of these sample tubes that we were going to drop here, again, as a backup plan in case there's a problem in the future with Perseverance. And so this cache of samples, or this depot of samples, was actually, there was a workshop that was coordinated by the MSR Campaign Science Group last September, and some of you may have participated in that, and they deemed this depot as scientifically return-worthy in case there is some kind of an issue in the future with Perseverance. So here is then a family portrait of all of the samples that had been acquired at the time of depot formation at the Three Forks Depot, which basically was finished on 28th of January 2023, so just earlier this year. And what I'm showing here is essentially to show you the diversity of rock types that's represented here in our collections already. And what you see here are swatches. Oh, I'm sorry. There are swatches of 2 or 3 panels, of which basically the leftmost panel that's outlined in red, that's the abrasion patch that Perseverance makes on each of the rocks before it does the sampling. And these are about 5 centimeters across, just for scale. And once that abrasion patch is done, there's some proximity science that's done that tells us about the chemistry of these materials. And then we decide, yes, we're going to go and sample, and we sample at a different site, not at the abrasion patch. We sample at a different site. And so for most of these samples that were collected before the Three Forks Depot was made, there are 2 samples, so pairs of samples that were collected in each case. And you can see here the photo of the tops of the sample tube. So you're looking down the tube before the tube is sealed. And this is about 1 centimeter across. And so you can see at this scale a diversity of textures. Some of these are igneous rocks. For example, these ones right here, as well as over here. These are all igneous materials. And then there are some sedimentary rocks like these ones right here. And I'll show you some close-ups in just a minute of some of these samples as well. And this one over here, by the way, I just wanted to mention, this is the very first sampling attempt that was made by Perseverance. And you can see the abrasion patch here. It's got these holes in it. It's an incredibly weathered sample. And as it turned out, they took the picture, and of course they sealed the tube, and then the data actually came back after the fact, and we looked and saw, oh my goodness, this is an empty tube. As it turns out, this is our serendipitous sample of the Martian atmosphere, and so it was a learning experience for us, and we have a sample now of the Mars atmosphere as well, which is fantastic. So this actually, because all of the samples can't fit all in one map at this point in the game, I'm showing here some of the samples that were these are now collected after the Three Forks Depot, except for the ones, of course, the ones that I've outlined in green dashed lines. Those are basically include one of the rock cores from that rock was deposited in the Three Forks Depot. And then there are 3 samples here, this one right here, and this one, Mellon and Otis Peak. These were all samples that have been collected up here in the Delta Fan. And again, this is a sedimentary rock that was collected right before we got onto the fan. And then this one is a sandstone. This one is a conglomerate. And so I'm going to show you sort of really quickly whip through some of the close-up images of some of these rocks, just to show you the diversity of incredible materials, and just to get you excited about the samples that you could be analyzing in your laboratory here soon. So I want to tell you here, first of all, about this igneous rock, which basically has pyroxene and plagioclase for the most part, but it's also got some salts in it, which we think there might be some sulfates, some perchlorate, some halides, and so this is a pixel image of this rock, actually, and it shows, you can see that nice interlocking igneous texture here, mostly pyroxene and plagioclase. And then this one is another igneous rock that was collected, and this is an olivine cumulate rock, mostly olivine, but it's got a lot of secondary carbonates in it as well. And in fact, what you can see here, this is another pixel image of this rock. You can see this beautiful igneous texture of pyroxene surrounding olivine, the classic poikilotic texture. And here, in fact, you can see resolved here are some of these melt inclusions in olivine. And so you can see that there are going to be these melt inclusions that you'll be able to analyze to get the composition of the magmas that formed these rocks, and possibly might even contain some volatile components that could be analyzed as well. Here is the first sedimentary rock that was collected, and you can see here the top of one of the samples that was collected. You can see it's a detrital sedimentary rock with lots of clasts that are visible here. Here's another one. This is actually a super exciting sample. This is one of the finer grained materials that was basically either a siltstone or a mudstone. And it also showed a very, very strong fluorescence signal, indicating perhaps that there's quite a lot of organics in this, but that has to be confirmed with laboratory analyses once these samples come back. And then this is another sedimentary rock. This is a coarse mudstone. And it also has some zircons and bedellites, which can be age dated, hopefully through some of the analyses that will be done once these samples come back, and has a relatively weaker fluorescence, so potentially indicating lower abundances of organics in them. And this is basically showing now it's a separate drill bit for sampling regolith, and so this was a sand dune that was sampled to collect some of the regolith. You can actually see the top of the tube here for one of the regolith samples that was collected, and the fragments, the little rocklets that are part of this regolith. Here is actually another sedimentary rock that was collected, a very fine-grained sedimentary rock, somewhat similar to the other fine-grained mudstone, but it has a lot more sulfates that you can see here, the whitish mineral that you see. That shows incredible amount of secondary alteration that's preserved in this particular sedimentary rock. And here's another medium sandstone that was collected. This is also a single sample that's, again, on Perseverance, not part of the Three Forks Depot. And it has a lot of carbonates, a lot of carbonate cements in it, recording possible, again, water activity in the sample. And then finally, the last sample that was collected and sealed is this one it's from part of the Pebble conglomerate, a boulder. And it has, you can see the beautiful, lots of different clasts, lots of different pebbles. It really is like a little jewelry box with lots of different gems in it, and really records a diversity of materials that potentially could have been brought into Jezero Crater from other places around the Jezero Crater. I wanted to just talk very briefly about the examples of the kinds of science that will be enabled by these types of samples. One example, of course, from the igneous rocks that we have collected already. The igneous minerals, of course, we'll learn a lot about igneous petrogenesis, rock formation processes, magma and mantle compositions on Mars. We'll be able to do geochronology to date the events on Mars that formed this rock. We'll be able to conduct paleomagnetic studies to understand something about the paleomagnetism on Mars as well. And then, of course, this rock also contains these secondary alteration features that were produced as a result of near-surface interaction with liquid water on the surface of Mars. And so we'll learn about near-surface water chemistry, we'll learn about potential habitability, potential biosignatures in these materials. And then the last example is from a sedimentary rock. This is from that particular fine-grained sample that has a lot of sulfate in it, the Kukaklek sample. And you can see here some of the siliciclastic grains in this that we can allow us to do some provenance studies, the kinds of rock types that may have contributed to the material that formed these sedimentary rocks. We'll be able to perform weathering studies. Geochronology will be possible on some of these grains. And then these clastic sulfate grains sulfate veins and VUG sediments, which will tell us a lot about past surface water geochemistry on Mars, as well as potential biosignatures, habitability as well. And you can actually, if you look closely at some of these veins, you'll see there's multiple generations of these sulfates in this rock. And so there'll be an incredible amount to learn from all of the history that's recorded in these rock types. And so I'm going to finish by just saying, these are real rocks that we have already collected and we can bring back. And I hope that you can imagine that it'll provide an incredible treasure trove of information that we're seeking about Mars and generally about rocky planets and the evolution of rocky planets in our solar system and beyond. I just want to say on a personal level, as a graduate student, I studied Martian meteorites in my laboratory, and I always dreamed of a time when we could bring back samples from Mars and analyze them sometime, hope, in my laboratory. And I just want to say, I hope by looking at these rocks, you can imagine analyzing these in your laboratory. And when I say you, I'm really talking to some of the junior colleagues here, our graduate students and postdocs that hopefully are excited to be part of this because this dream is about to become a reality. And so, we have the samples in the bag. We've got the technology to get these samples. So let's go get these samples back. So if I understood you correctly, you're saying that by putting boot prints on Mars, you would destroy the possibility of actually doing organic chemistry and learning about the origin, potentially, of life on Mars, those types of questions?
Not to say that it would happen, but there is a risk of that.
So that is part of the reason why I think it's so important to bring these samples back ahead of human exploration, ahead of astronauts going there. Because I think we'll learn a lot. There is a lot to be done and a lot to be learned from synergies between human exploration and robotic exploration. But I think bringing these samples back ahead of humans going there, we will learn a lot more about potential hazards. We'll learn a lot more about the environment there, and we'll know how to plan for future missions once we actually get those samples back. So I think it makes it all the more important, I think, to really get these samples back through these robotic means ahead of human exploration.
Yes.
Hack Sweeney, University of Tennessee. There's a strategy that's been used for planetary exploration, which is study them from orbit, then go to the surface and study them from the surface, and then bring the samples back. And that's obviously the strategy that we're using for Mars. For small bodies, this seems to be collapsed into, all of these strategies seem to be collapsed into one mission. For example, MMX looks like you're doing all of that, but with one spacecraft. My concern is that we're going to miss, by doing that, we're going to miss some of the geologic context of these samples. And without a really good geologic context, the samples are more like meteorites. We know they come from this body, but we don't really have the geology. I'd just like your thoughts on whether or not we can do this well enough in one mission.
Okay, let me start with MMX will go to a small body, which is Phobos and Deimos, and then land it on one of the body like Phobos. And they have also deployed a rover on the surface of Phobos. And it's risky and also very expensive. And then they may have a chance to have lots of things happened. So, but it's like Phobos is kind of unique compared to the other small bodies like asteroid stuff. So Phobos missions, the MMX way of doing is kind of straightforward, at least for Phobos, that has still, I believe,
geological diversity, so that orbiting around the Phobos first, and then deploy a small rover for the in situ formation, then finding out the actual landing sites to represent the surface material, then they come back. So, but that kind of strategy, I believe, may not be always true for the tons of small body asteroid like Bennu, Ryugu, and lots of like Psyche target, Trojan asteroid, yeah, something like that.
Yeah, I would comment that geological context is kind of tough to do in a RoboPile. But you know, when you spend, like we did, spend 2 years in orbit, have people understanding sort of the regional geology of Bennu, understanding how boulders have migrated, how it achieved this spinning top orientation, you know, that's providing you your context. And when you're imaging basically every rock on the surface of Bennu down to the millimeter scale, where you can recognize breccias, where you can recognize veins of alteration, all the things that we've seen in that sort of orbital campaign, I think it gives us a really great geological context for the samples we're bringing back.
So in the case of Hayabusa 2, so we know that one mission cannot do everything, but so we did sampling at 2 different locations. That is to understand some geological context. And as I mentioned, the Touchdown 2 was made nearby the artificial crater. And then, so through the analysis of the Touchdown 2 samples, I didn't have time to mention that. So we found that the samples from Touchdown 2 may come from about 1 meter deep of the surface. So doing the multiple sampling at different locations, we still have chances to understand the geological context.
And I guess I'd also add, I mean, the lesson from Hayabusa 2 is a lot of these samples are brecciated at an incredibly fine scale, and you're sampling lots of different lithologies that have come together, you know, at a very small scale.
Yes. The microphone is coming your way.
Thank you. Hi, I'm Liz O'Mara, just here because I'm a rock chick and I like meteorites more than some people. Here's what I'm wondering. Would you expect to find samples that either would fill in or expand the periodic table, stuff we've never seen before?
So I think what we've learned from studying meteorites as well as materials that we have in our collections already is that the elements that make up the different things in our solar system are all, the building blocks are all made up of the same materials. The elements are, so we don't necessarily expect to find new elements, but the combinations of these elements to form minerals and then the rocks that we get, those can be different, and they do record some of the differences in the kinds of environments in which they form, which are certainly different from those in many cases than how they form on the Earth. And so, yes, the minerals for sure, and some of the actual minerals that form, I mean, the basic things like plagioclase and pyroxene that I was talking about before, you form the same kinds of minerals here on Earth as well, but you can, by looking at the trace chemistry of those, infer that they formed under different conditions. But yes, I mean, the building blocks, the elements, they're all the same. And that's part of what Shogo was talking about as well, in terms of, you know, the solar system being made up of these complement of elements. And so the meteorites actually have the same elements, but the minerals are somewhat different. I don't know if others want to add anything.
Totally agree.
Ginter Kletechka, University of Alaska Fairbanks. I was excited to see that finding the deuterium in Hayabusa samples, and I remember there was a lot of talks before exploration of the moon, like a South Pole, that there may be also a location of tritium deposits. So I was wondering if you attempted to look at tritium in Hayabusa samples. Tritium.
Sorry, I cannot hear you well. So you talked about...
Tritium.
Oh. I don't think we tried to detect it during the sample analysis phase because we focused on to understand what Ryugu is. So, but the sample is now open to the community. So some people may want to do that.
And my second question is about Shigai, the dead matter that may be coming out from the Mars surface during the ejecta in old times. I thought that when there was supposed to be life, it probably was shielded by the magnetic field of Mars, which means that if there will be any Shigai on the surface of these two moons, those samples will be probably magnetic. And I wonder if there would be any, because there's a suite of instruments on that mission, if there is a magnetometer involved.
Okay, I haven't studied the magnetic signatures of the ejecta from Mars on the Phobos, but like the curation team, I'm a JAXA curation. The curation team think of the curation facilities ready for the sample who has the magnetic signatures or not, so that like same with the Hayabusa 2 curation instruments, that we carefully choose the device, even it is a metallic stuff, and then we demagnetize it before use it. So if something magnetic anomalies or signatures is in the sample, even with the CI or just minerals in it, I think the MMX curation team could provide these samples without any contamination of the magnetic anomaly stuff. Yeah.
Yes.
Hi, Lars Bohr of Lawrence Livermore. I have a question for all four of you because your missions are in different stages. And as somebody who works in an analytical lab and does measurements, I wonder if you would briefly describe how you either prepare for the samples to come back or are anticipating preparing for the samples to come back in the context that many of these samples are either in a form that we haven't seen before or have characteristics that we haven't seen before. And so we're going to have to develop, and probably have developed, some techniques that we don't typically apply when we analyze meteorites. And so how did the missions that are returning samples and analyzing them now, like Hayabusa, or going to in the near future, like OSIRIS-REx, or in the more distant future, like MMX or Mars sample return, how did you prepare your community to make the measurements that you deem necessary to complete your science?
So for Hayabusa 2, the most difficult point was that we had no idea how much samples coming back because the spacecraft had no way to measure or no way to look at the samples. So we had to be very, very flexible. And so soon after the samples were found in the sample container, so we had about 6-month interval because during which JAXA curation team worked to describe the samples in the nitrogen-filled clean chamber. So during that phase, of course, before that, so we had an international analysis team and had a plan to what we're gonna do. But so soon after we saw the sample and soon after we knew the amount of the samples, we really intensively discussed what is going to do. And then during that period, so we did analyze 2 mysterious particles found outside of the container. They were actually Ryugu grains, and we found soon after, so just after we saw the samples, they are CI chondrites, chondrite-like materials. So that really helped us to think about what is the analytical strategy. That is what we had for HIAPS-2.
Yeah, I mean, I would comment that we have a very mature sample analysis plan. You have a big science team with experts in most of their analytical techniques. You know, part of the reason you select team members are expertise and the kinds of analyses that many of the people in this audience have been doing, you know, since graduate school. And you want to make sure that the samples are protected and curated so that when new techniques come up, you have access to material that is still pristine and still available for these new kinds of techniques. That would be my guess.
Okay, next phase is like a phase D of MMX. Okay, yeah, MMX case is slightly different from the OSIRIS and the Hayabusa-2 because during the development formation stage of the MMX and formation stage of the older missions, Ryugu and they actually OREX and Hayabusa-2 team did not know anything about the target body other than just a white dot. They are Ryugu and Bennu. But for the MMX case, the Phobos and Deimos are well-known target body. We have tons of the remote sensing data already. So we could use them to see what kind of sample analytical strategy that could meet the mission requirements and mission goals. But we should be ready for contingency case, and we still do not know the physical properties of Ryugu regolith and grain size and anything other below the reflectance features of the surface. So slightly different, but it's like we should be ready for the nominal case plus a lot of contingencies. It's kind of a trade between like budget stuff as well. Thank you.
So for Mars sample return, you know, we have the luxury of having a great team of scientists that are actually part of the Mars 2020 team already. People, you know, like Chris Hurd, who's here, you know, part of the Return Sample Science Working Group. It's a group of sample scientists that are involved in the sampling of these materials. There's a lot of documentation, of course, of each of the samples that's collected. We know, as you saw from some of the pictures, and there's a whole lot of data behind each of those images that I showed you. There's, you know, geochemical, petrological, textural information that can really, I mean, we know how much sample there is, we know what's in those samples to a great extent. Not everything, of course. I mean, that's why we're bringing them back, of course. So there's, to some extent, we do know kind of we will know what we're going to be bringing back. At the same time, I think, you know, there are community science groups that are being organized, for example, like the measurement definition team that is going to be considering, you know, what are the kinds of analyses that can be done on these samples, and what is going to be highest priority, what is going to be time-sensitive analyses, what are going to be some analyses that are going to be sensitive to sterilization, perhaps, that might be needed for some of these samples. And so there is some planning that's already taking place to start to think about the kinds of analytical capabilities that we're going to need to be ready for when we bring these specific samples back. So there's some time and thought being put into that already.
And I guess I'd like to add that, you know, you have these missions that take, you know, in the case of OSIRIS-REx, you know, 16 plus years, and you have an initial science team. Those science teams, you need to be sort of multi-generational, and it's nice that NASA does sort of a participating scientist program, and in our case with OSIRIS-REx, we use the participating scientist program to sort of fill in the holes, because you can't anticipate every instrument kind that's going to be used to analyze these samples, new kinds of analyses that you hadn't anticipated 10 years ago, because the path of technology is just so wonderful in most of our analytical techniques. You need to be flexible. And I think that's what you were trying to get
I
at,
think
Tomo.
one thing that I really want to underline, actually, that you already said, is that these samples that we bring back, and that's one of the powerful things about sample return, is that a big fraction of these is actually curated and stored away for future analyses, and so that really does allow you the advantage of time and the ability to actually develop techniques later that could be brought to bear on these samples as well.